And in the description, you will also find some references to some of my GitHub repository. One of them is this one, which is actually an illustration that comes together with the first video. I'm trying to implement some simple, very simple application of the algorithm I'm presenting. So here you can see a car which is driving in a 1D, very simple environment. The goal again is just educational, trying to make some illustrations about the intuitions and the concept I've been describing in the first one. So have a look if you are interested. The second reference is a paper I've been writing last year, again available on my GitHub. The idea or the motivation was to summarize, or for me at least, to kind of structure what are the common approaches when it comes to organizing the decision-making part for autonomous driving, and together with it give a quite rich and I think recent and state-of-the-art literature review. So here are all the references about what people can do and what people are doing when it comes to decision making for autonomous driving. So again, the link is in the description of the video. So the plan for today, I've been mentioning it shortly. First, we have a look again at the concept of MDP I've mentioning last time, and directly go to an example, a concrete illustration. What does that mean? How does that work when we try to implement that with a Model 3 agent trying to drive in the car simulator? And then we'll have a look at a second way to learn the policy. In this case, we'll be looking at an expert and, for instance, a human who is driving, and then say, I want actually to imitate the way this person is driving. So two branches of IL. First one where you want directly to learn the policy, so direct method, and second one where you decompose the task. And first say I want to recover some reward function and then learn a policy based on this reward function. So we'll be covering this topic. I will be trying to share what I've been learning and obviously give a concrete application, an example. How can we implement and apply this concept in some examples? I already want to say that these examples are not perfect. I've been doing some mistakes, and I think it's worth from an educational point of view to leave this mistake in the slides and then to say, okay, this was not a great decision, a great choice in the design. It doesn't work quite properly, but still have a look at it and say next time, or maybe here, this is how I would do that better or in a different way, and share that with you. I think it's also worth. And this is how reinforcement learning works, right? It's trial and errors, and you keep the errors in the experience replay. And last but not least, having a look at some of the state-of-the-art, very recent papers I've been reading, and I really want to share them with you about decision making in autonomous driving. Before I start, I want to make two mentions. The first one is, I don't call it laziness, but I didn't write on my own the formula in the slides. The reason for that is I want to be consistent with the papers I've been reading, and almost none of them is having let's say, a conventional notation scheme. So many are using W, and then some are using some phi, some are using some theta, and since you will be reading papers as well, I thought this may be a better way to leave them as like this, because people are using different notations. Don't be afraid if the notation change. I will try to not to mention that, but don't be afraid by that. A second short mention is about some of the graph I will be presenting. I just want to say that, for instance, on the first two graphs here, there's an orange plot, or an orange line as well, which is just the smoothed version of the blue one. So this is the same data, just smoothed with some smoothing window applied on it. Again, I will be mentioning that, but I just want to give a little mention right now before we start. Here we go. So Color Simulator, it's an open source simulator for research in the topic of autonomous driving. It's a great community, really active. There are already a lot of papers trying to do some reinforcement learning, some imitation learning with this simulator. So if you haven't, have a look at it. It's a very brilliant and a nice team as well organizing that. Quite responsive when it comes to helping you. I really recommend. So you see is just a screenshot of the scene in Carla. What we'll be doing is we'll be controlling a car. This is our agent, and the goal will be to drive in the road and to achieve some of the let's say scenario that are defined in a separate Carla plugin or Carla repository, which is called the scenario runner. So you have a couple of scenarios being defined. We'll be doing the one about following a vehicle. So this is maybe the most basic task you want to achieve, following a vehicle. And again, we'll be using this Carla scenario runner tool. Just want to mention also, Deep Drive has recently announced a partnership with the company called Voyage, don't know how to pronounce it. Just to mention, because it looks similar based on graphic, it's also based on the Unreal engine. The difference at first sight, I haven't been deeply reading about the details, but at first sight, you see there are a gym environment. So it looks really convenient and appropriate if you are doing some research for autonomous driving about reinforcement learning, just to mention. Back to Carla. So Carla, the task, if you are to control the agent, Carla wants you to give some object, which is the Carla vehicle control. It has a couple of attributes. Two of them will be interesting for us today. The one about the acceleration, how do you press the pedal for accelerating? This is called the throttle. It has values that are continuous in 0, 1. And then steering is about the steering wheel, obviously -1 to 1, depending if you want to go left or to the right. But again, just mentioning 2 points, the acceleration is not the throttle. So if your module is about to decide some velocity profile or acceleration profile, this won't be enough. You could obviously try to forward the acceleration, but what is really expected by the Carla side is the throttle. And the second thing I want to say is that these values are continuous. In this case, for throttle, it's between 0 and 1 in this interval. So to formulate the problem, we'll be making a very strong assumption. This is called path velocity decomposition. It's commonly used, and this is the following. On the left part, there will be a module dedicated to deciding the steering, and on the right part, there will be another module, independent, whose task is to define the throttle value. So this is how it works. From the map, and given a location, you compute the route, so which intersection you want to travel to, and then you have a look at the predefined path on this route. Then based on this predefined path, you want to output a steering value. Either you do it directly, this will be the right part of this lateral decision block, or you say I first want to extract to sample some target waypoints, and then you want a PID, for instance, that is tracking and targeting these waypoints and deciding the steering consequently. On the other end, and this happens at the same time, you have a list of objects. These come from the perception module, and then you extract a vector from these objects. It's, let's say, called your state, and based on that, you make the longitudinal decision. That means you want to decide, you assume there is a valid path for you, and then you want to choose the longitudinal acceleration. Again, either you do it directly, or what you can do is decide the target speed, and then implement and then use a PID to derive what throttle or brake should you have in order to reach this target speed. So just to mention that, we'll be focusing on this longitudinal decision. There will be two versions of our agent, one working with target speed and then PID, and the second one will be directly learning the throttle. Just to remember, the problem is reduced to one spatial dimension because we are decomposing these two tasks, and this makes the problem way easier to solve because of the lower dimension in both the action space and the state space. So you have noticed that the decision is based on some vector which contains information about the objects that have been detected. In other words, and this is what I want to say here, is that we decompose the problem. We take the decision part away. We say this has been solved by another module. We take, let's say, the application part of the command away. This is done by Carla simulator. It takes the throttle and then moves the vehicle for the next step. And this decomposition at the end leads to this task: learning to decide, learning to make decision. What should I do in the next time step in terms of steering and in terms of throttle? I just wanted to mention that, and I will go back to this concept again in the research paper section. So reminder about last time, I've said that reinforcement learning was an area of machine learning concerned with how software agents should take actions in an environment so as to maximize some notion of cumulative reward. Again, all the underlying terms are important. They have been explained last time. What we also said is that typically this environment is formulated using a Markov decision process. So it's the, let's say, the way to model the problem, and the RL part is the way to derive an agent that takes action. Say it another way, it's about problem setting. When you use this MDP, you formulate the problem, and then the solving part, solving the MDP can be done. This is not the only option with reinforcement learning. This is, let's say, one of the main messages I gave last time. So what did we say last time about the Markov decision process? We said this is basically a tool for formulations, to formulate a problem, to model a problem. In this case, to describe the task. The task here would be to drive, and what drives mean in this case is just decide of longitudinal control. What do you want to do in terms of acceleration? This is the task for today. Then we introduce the concept of policy, which is a mapping. This is a function from state to action. So usually people use the symbol pi for the policy. The pi takes a state. State is just a description of the current situation. And based on that, the agent should apply the policy which tells him the action, what to do. Let's take an example. Let's assume the state is composed of two elements. The first one tells you how fast you are driving, the speed, ego speed, 30 km/h. And the second one is the distance, that is from your car to the next crossing or to the next, let's say, stop sign, 60 meters. Then based on that, pi is applied and pi answers an action. Let's assume this gives you the maximum throttle you can apply, 1. What happens? Then a transition happens. And in the transition, you have two elements. The first one is it takes the agent to the next state. In this case, since you are accelerating, you expect the speed to increase. That is what is happening. So the ego speed goes to 35 km/h. And the second thing is you keep moving forward. As a result, now the distance is only 50 meters. That's the first element of the transition. It takes the agent to a next state. The second thing that happens is that the agent is receiving a signal for that transition, which is called a reward. In this case, I don't know, it's an arbitrary number. I could have put -1, 1, whatever, depending on the safety aspect, the efficiency, because you want to reach your goal, whatever. Just have in mind, this is a signal that is given to the agent at each step. That is important, at each step. What I want just to mention is that in this transition, you have two, let's say, underlying functions. The first one that takes state action and output the next state. And the second one that decides for the reward. These two functions can be unknown or can be known to the agent. And that's the difference between learning. If you have no idea what will happen when you press the acceleration button, you have no idea that it will cause the speed to increase. So you have to learn it. And the second case is that you know this dynamic function, you know this reward function, and what you can do is plan on your own. You don't need a simulator to make rollouts, and that leads to a totally different set of algorithms, just to mention the difference between planning and learning. This is one-step process, and this is actually repeating many times. So imagine you have the agent on the left, you are given a state S, you have to take an action A, you pass that to the environment on the right, and then the environment takes these two information and decides or apply the dynamic step. It can be deterministic, and it can be stochastic. Anyhow, it returns the new state you are in. And together with a reward, this little signal, this scalar number that comes with the new state, it's called reward, sometimes it's called cost. So why MDP? D for decision, because you have to take action. We'll be mentioning Markov in the next sections. And process, because it repeats. You see, this cycle can be repeated again and again. Now I want to give a little bit extension to last time, because I didn't mention the features in the previous video. You have this pair of state action, and what you can do is from them, or from this pair, define a couple of features. What are features? Well, first, the good news, people don't agree about the notation. It's sometimes called phi, I think it's phi or phi, f or psi, or yeah, these are the three I've met in my research. Basically, it's just a mapping. You take these two information. So let's imagine in this case, the ego throttle here is just one element of the action, so you don't actually use the state. This is the input of your function, and you return a scalar. In this case, what you are doing is saying, I apply a threshold, 0.2. If the throttle value is above that, I return 1, otherwise I return 0. This is what it's called, it is int for type. It's just extracting information from this state action pair. A maybe more complicated one, feature acceleration when you are closed. So here again, you take some information about the action you've decided, you take some information about the state you were in, distance to other, and then you decide, well, does the previous feature, so are you accelerating in it? And if you are accelerating and at the same time the distance is quite small, again a threshold, then I return 1 and then I return 0 otherwise. So just to mention, I will be using some feature in the following, just a mapping. You extract information from this pair of state and action. I'm saying that this process repeats again and again. So one could have the idea of collecting these pairs, state action at t0, state action at t1, and so on and so on. This constitutes, or this is building then a trajectory. The trajectory is a collection of state action pairs that happened sequentially. This is why it's called a decision process. You have to make successive decisions. You could have the idea of doing the same with the little signal that you get, the so-called reward. You will have a look at each time step. So at time 0, I get a little reward R, at time 1, another one, and so on. Here, the gamma, so this symbol, you can think of it as 1, it's called the discount factor, and it represents how value you put to the future compared to the present, so you can play with that value between 0 and 1. You can, for the moment, assume this is 1, and then you just see it turns to be the sum of the collected little reward signal that you collect at each step. Then the idea of this sum, it's called the return, discounted because of gamma, just the sum of that over an horizon of size n. Well, what can I do with that? This is just when I apply a policy, I get a trajectory and I get this return for this particular trajectory. But actually, this is coming, or it's similar to having sampled that from one distribution, which is distribution of a pi, because it comes from this policy. And you can formulate or you can define an object which is called the expected discounted return. And it tells you on average, if you follow pi, how much return you are expecting to get. And this is why there is the expectation sum there. Important to remember is that it's for a given pi. It's a function of pi, and now it will help us to define the task. We have an MDP. What does that mean, solving the MDP? The MDP, solving the MDP means finding the optimal pi. So we are interested in finding a policy. What does optimal mean then, we'll ask? Well, optimum means better than any other. Okay, what does better mean? We need some comparison operator to compare pi 1 with pi 2. And this comparison operator could be using the previous line. Now we have a quantity and we'll be saying pi 1 is better than pi 2 if the expectation for pi 1 is greater than the expectation for pi 2. And that would leads us to this concept of solving the MDP is about maximizing the expected discounted sum of reward over time horizon. So how to solve, how to find the optimal policy now? I really want to refer to the first video where I detailed the way to do that. Just here mentioning the value-based approach. What does that mean? The goal is to find pi star, and we said that pi is the mapping from state to action. So why not learning a function, maybe parameterized, that maps from state to action? This is the first option, the direct option. And then there is an indirect option, which says, I first want to estimate for each state and for each action some Q values. Let's say this is an intermediate task that I fix to myself. First find these Q values, and then one task and then another one, which would be from this one, actually make the decision, decide which action I want to take. And this is called the value-based approach, family of algorithms. What are the Q values? So maybe go back first to the expected sum of reward, which is the expected return that we have. Again, I just want to remind that it's a function of pi, or it's for a given pi. And then we can define the Q value. The Q value is attached, or it's linked to a given pi and tells us if you start at S state, and if you start doing action A, and after this pair, you always descend to pi, if you do all that, then on average, you should expect to collect that amount of return. This is what is the intuition behind the Q. We can also abstract the action and say, if you start at state S, and from there descend to pi, how much return are you expecting to collect? Well, the answer is given by that. So just to summarize, and let's say a small conclusion, there are this notion of Q values. This is a function of pairs, so it takes S and A. It can be put as a table, because if this is discrete state and discrete action, you can list all the possible combination and you will get some values in each cell. This is what we'll be doing, and it tells you how good is it to take action A in state S. And the last but not least, a Q is always associated to a pi. So it's Q pi of S and A. All right, so that was let's say the reminder of the previous video where we introduced the concepts. Now, let's imagine a very basic, simple example, and let's try to apply these concepts to this example. What MDP do we want to formulate? Well, the state space will be composed of a component describing the distance to the other. Just remind that we are dealing with the scenario of following a vehicle, a part of the scenario runner, together with the ego speed, which is the current speed of the controlled vehicle. So it might be, like this will be in a meter per second, this will be in meter. Note that that's all in our state. You might be wondering, shouldn't we include the previous speed? Shouldn't we include the, I don't know, distance that were between us and the vehicle back 10 seconds in the past? At least not in an MDP. This is where the M comes from. This is the Markov term, which says that the future is independent on the past given the present. What it says is that this information should be large and enough, good enough, and all the information is captured inside this term, and you don't need anything else in order to make a decision. A common, not a trick, but a common approach is to stack. So you can say my state is composed of, let's say, the last 4 vectors which capture the distance and the velocity. So you can make that, and then you take the previous, let's say, 4, and this is a stack, and this stack is your state. This might also be an option if you want to keep the MDP structure, but have some, let's say, relaxed Markov assumption. What's just to mention. All right, so we need to output an action. We'll be first outputting an intermediate action, which is the target speed. Do we want to target speed 0 km/h, or do we want to target the speed 50 km/h? Again, there are more or less, or this 50 could be 60, maybe 40, whatever. What I want just to say is that this is yes or no. This is binary decision, or at least this is a discrete decision. This is not an interval. The output of the first action is one number inside a set. And then, based on that, a PID controller, which controls the, let's say, the acceleration by doing the following. It takes the target speed that is fixed, either 0 or 50. It takes the current speed, I don't know, 25, current speed of the vehicle, and says, in order to reach the target speed, I want to apply this throttle. So on theory, this is between 0 and 1, and this is, on theory, a continuous interval. We will see from the experience that the PID controller will be mainly either choosing 0 or choosing 1 in order to reach the target speed, just to mention. So that's the first half of the MDP definition. So the MDP needs also a reward function. The transition, I don't define it because it's the job of Carla. This is something that is unknown to the agent. But for the reward function, it's also unknown from the agent, but we need to specify what the task is. And that's where the second strong assumption comes, is that I'm saying that the reward function is a linear combination of features. That means that it's a dot product between weight vector and this feature vector. Again, one feature is just extracting information from S and A. Let's go through the features I've been defining. I start with a constant feature, which is equal to 1. This is why it's called constant, is independent of S and A. I just want to put 1. The reason for that is you want to prevent the agent not to do anything. Can you imagine? One agent could say, I want action, don't do nothing at all timestamp. You won't move from S0. And let's say the benefit, theoretically, is that you won't encounter any risky scenario or risky situation where the reward will be negative. So in order to avoid these negative penalties, one option could be for the agent not to do anything. And you don't want that. One way to avoid that is say, I want to penalize. So this will be weighted with a minus in W, a minus contribution. You want a negative contribution or signal for per each time step, whatever the decision is. The second one, I have not been mentioning it yet. It just extracts some information from the state, not the action. It extracts the two, actually, the distance from the other and the speed that you are. And it's saying the feature activates, so goes to 1 when you are close to the car, to the other car, with a given speed, so higher than a threshold speed. And this is obviously something you want to avoid. This is why it's also in a red, orange-like, but a more sharp red one. You want to avoid that really. A third one, you also want to penalize it because you want to avoid that situation, is the one I've been mentioning. Are you accelerating? So is the ego threshold activated when you are close to the other one? Again, you want to avoid that. Fourth one you want to avoid again is not to drive faster than the speed limit. So put it another way, not to accelerate when you ego speed, when you're driving already fast. And the last one is about something you want to favor, you want to reward, you want it to happen as much as possible because it represents efficiency. The three here are about safety, and this fourth or this fifth one is about efficiency. And you already see that reward function when you design it, you want to trade off, you want to make a compromise between safety and efficiency. And this is why it's bonused. You get a positive for it so that it drives, let's say, as fast, or it reaches the final point as fast as possible. An important point I want to make is that in the first, or in the definition of features I'm introducing right now, it's about binary features. This is a choice I made, and to be honest, you will see that in the following, this was absolutely a bad decision. Really not great choice to do that. I won't do that again if I were to repeat that, and actually I will do another version where they are continuous values instead of binary. The reason for that, for instance, just take that one there. You need a threshold. I put 0.2, so if you are 0.21, it's the same for the feature point of view as if you are 1.0. So you can already see this was losing or removing or erasing all the information, dropping that, but yeah. This was the first implementation I made. I wanted to share that with you, binary features. And the weight vector is the following. You want to highly penalize these red two terms. You want to favor that one with a positive one, and the two as a negative, again, to deal with, let's say, regulate. This is about traffic law and a little bit of speed as well, the traffic rules mainly, and this is a little bit of the trick of efficiency. So this is the reward function. Now let's go to the training. So for the training, I will be first launching the video because it's quite long. What I've been doing is you start from scratch. So let's imagine first the Q table to be empty. This is like there is no row in the table. The table is representing here. So you see at the moment we have 1 and 2. Now we have a third one. So we have 3 state being on counter. So 1, 2, 3. Now we have a fourth one, and so on. So the agent is by experience discovering new and new states. And for each of these states, so these two rows represent the state. So for each of these states, it tries to assess how good it is to take the value A0 being in being in S. This is the QSA0. And how good is it to take A1 being in S? This is why you need a S, which is there. And it does that for each of the states it encounters. The training is structured as follows. You start with a random policy, meaning you take random action. This is actually happening. Here you can see the throttle bar. You can see that is evolving quite fast. I will come back to this detail a little bit further. And you can see also it jitters because it takes random action. It's not consistent with time. Here we are driving at 4 km per hour. It doesn't have still the idea of speeding up in order to reach the desired speed. There will be a timeout. You can't see it really well, but there is 1 minute timeout. After 1 minute, the episode terminates. And what I've been doing is I've allowed 3 episodes for the agent to in order to collect and gain experience. We will be in a short period. It will be first termination of the episode. So I will be reducing the epsilon, which is how much of randomness do you allow in your decision. I will be reducing it from 1, which is the case here, to 0.66 or to 2/3. This will be the second episode, and then from 0 to 66 to 0.33, which is the 1/3. And that's it. I don't train any further. I allow only 3 ways or 3 episodes on this long straight road, and it should be enough for the agent to build its own queue table. So you see at the moment we have 5 states. I will stop there, but at the end you see this full table in which the agent has collected his value. You can see already 25, 20, yeah, 29, and so on. It's not constant, but at least it goes a little bit better than the fully random agent. That's the train. So at the end of the training, since the state space is only of size 2, you can plot the argmax of the QSA. So the state consists of the speed in kilometer per hour in this graph or in this plot, and it consists in the distance to the other. So you see here we were very close, here we were very far away from the other participants. I've not been mentioning, but I discretize quite largely the 2 components in this state. In other words, from 0 to 20, this is 1 bin, then and so on. So you can see it's quite a tough, or at least a quite important decision to make, but it allows the state space to stay very small, which is not bad from this very simple tabular example. And now what's about the plot? What's about the plot? You can see here the two actions that are possible. And I said within this table, we collect the information, how good each action is given one state. You have 2 possibilities each time, and this table is just showing the best one. So here, for instance, if we consider that one there, we were at distance 40 meters, and then we were having a speed which is center around 20 kilometers per hour. So the agents learned in this case, if I were to act optimally with the Q values I've been learning, I would be selecting the action A1, which means, let's say, accelerate, or at least target higher speed or high speed. That means you want to accelerate, and that applies to all this area, which is actually the area where the other is quite far away, so from 40 to 100 meters, and the area where at the same time you are not driving too fast, so you are below the speed limit, which is defined by Carla by 30. So in all these cases, you would like the agent, or the agent would like to target a higher speed. On the other hand, if you are in this portion, then what you want to do is to slow down. The reason for that is, as said, you're above the speed limit, which is 30 in the Carla tone. And a third one, which is that one there, which is you don't want to accelerate being in this situation. The reason being you are close enough, and in order to keep safety, or if the other is already stopped, like this one, it's maybe cautious enough and a good idea not to speed up and to target the zero speed, which is represented by action A1. So that's the Q table, the argmax of each element, or each row, sorry. And now we'll be doing testing. So we won't update the value anymore, and the values anymore. We'll be using them and try to see how the agent performs. So that's the testing case. I've been leaving the agent on all the following leader scenarios that are available in Carla. So there are around 10 of them in the scenario runner tool that is provided with Carla. This is the one where we were training on. And here, if you look at the colors on the left part, so in the table, they are actually showing which is the best action you want to take. You see that this was the example I took. If you were at distance 40, or at least in this bin, because it's discretized, and at spin 20, then the best choice is to take the action 1, which is I want a higher speed, or I want to target the maximum of the two possible speeds. Here you see the third block that I was showing or clustering, which is about the distance is very low, so I better have not to accelerate in this case. Yeah, that's it. The video is quite long because it goes through all the possible scenarios. This was the first one. What you can see if you work with the scenario runner, if this section you get the success part because okay, now it's gone by. It just assesses the agent based on did you drive within the timeout and did you drive without crashing. And if these two criteria are accomplished, then the scenario is considered as validated. And we have 1 minute to do it without crashing. Here's just the second one. Again, there are 10 of them going to different tones. You might say, okay, this is similar. Actually, this is exactly the opposite. So you see on the bird view, this is just the parallel street to the example where we were training. Can we say a word about generalization, because it's succeeding in all of the 10 possible configuration or tones definition in the scenario runner. Actually, we are each time extracting the distance and the ego vehicle. So although the scenario, or let's say the trees and the shapes of the roads and so on are different, I'm not sure we can speak about generalization as is the case for perception, because we already have extracted the information being supplied. Again, you can see success. So I passed through, but the 10 of the possible scenarios were accomplished. Here is another tool. So that concludes the first part. The motivation was give an example of the concept I was introducing for reinforcement learning and MDP. It was really simple. It's a basic application, basic problem formulation with these very large bean discretization scenarios were really simple, but already useful to take to step back and to give some takeaways. The first one, what happens if we don't, if let's say if we don't see a state during training, if we don't add this row to our table during training because we don't encounter it, and then we are asked during testing, what should we do if I meet this state? Because I'm currently in that, what should I do? Well, you already noticed that with this tabular version, you have no idea. There is no row saying you, in this state, you should do that. That's already an issue. Okay? You can't rely on extrapolation between states. You can't rely on, this is the reason why there are some, or one of the reasons why you want to use some function approximator, for instance, to cope with that for scaling as well. The second concern you can raise is what about the time frequency? Because I saw the gauge, this bar where the throttle was showed, and especially in random case where it was picking one randomly, was jittering quite a lot. So that means the agent is changing quite very, very often of action. Isn't it an issue? And actually, I did some modification afterward, but it was already good to mention. Have a thought about at which frequency you want the agent to act. A third concern you might emit is about generalization. What about the speed limit? You said this 30, but is it a threshold? Is it valid for any road? Your agent can't go to a 40 limit tone at all because it has been learning on a 31. That's not wrong, that's correct. And one of the options, and I will be doing that in the following, is instead of using absolute speed, like the absolute ego speed, why not having a relative one, which tells you the delta between the current ego speed and the maximum allowed speed for this particular tone. And if you move to the next one, you still have this delta, and you can work with this abstraction of the 30 parameter. That's an option. There might be another. What else can we say? The MDP definition. So this is a problem I defined for myself. It was not something available online. It comes with drawback. You have to define that on your own. You might make a mistake, and you might not detect that quite straightforwardly. An advantage if you can choose MDP that is already defined, especially if it's in the OpenAI gym format, is that other people are using it, so you can at least think that people are, let's say, it has been tested, but more importantly, you can compare with people because you are using the same simulator or the same MDP formulation, so you can compare your agent with what other people did in their work, which is quite important to have in mind when it comes to developing algorithms. A quick word about feature selection. It was enough to keep them binary for this case, was enough for the model-free agent to complete the task, but we'll see in the following, having them binary was an issue. It might look quite straightforward to design the weight parameter in this reward function. It was not for me. I spent quite a lot of time trying to fine-tune the parameters. Why so? Is because you want to trade off between safety, between traffic rule compliance, and at the same time efficiency. So you have three, it's a multiple objective optimization problem, and the only influence that you have is to play with these five parameters. And it's not trivial, and I can imagine when you try to scale, when you want to address more complicated scenarios, might become quite early a tricky task. And that's the motivation that brings us to the second part. Not starting from scratch, and rather from demonstration. That means you observe someone in the street and you want to, let's say, either infer the reward function, that would be one case, or directly learn the policy to drive as this person, similar to this person. And just shortly mentioning, when we will be doing why we will be doing this imitation learning part, and this is already the case here. Have in mind the sampling efficiency of the algorithm. What is it? It represents how much you need to interact with the environment, because there might be the bottleneck in terms of time for the training part. In this case, this is quite good actually. Only 3 minutes. In 3 minutes, and especially in 3 drives of this following leader scenario, was enough to derive a policy that could pass all the 10 other scenarios of the follow leading package, follow leading vehicle package. But it shouldn't be it shouldn't be too big, and it should be kept small, because at the moment I'm not parallelizing anything, and I can't make it work way faster. So having the sampling efficiency in mind. And the last 2 things, yeah, you want to, at least as a developer, or a designer of the problem, I was always thinking, why not incorporating, like manually hard coding some basic rules, like preventing the agent from doing that, or yeah, actually making it stop at the end instead of going and then having 2 km/h and then not managing to stop. Maybe you should help it or not. Yeah, this will be a trade-off we will have between should we rely on the weights and the exploration parameters and so on for the agent to learn that, or are we allowed to have a parallel mechanism that decides and help the exploration and ensure some safety guarantee, because at the same time you want generalization. I already pointed the fact about the 30 km/h limit. So that might take away for the first illustration part. Now let's go to imitation learning. So imitation learning, we said the motivation, not starting from scratch, and this is the idea. You want to learn something from observation. So you're observing some person, maybe a robot, maybe a human. Let's call this person an expert. So you have expert demonstration, and from that you want to learn something. The underlined word something is what model or what parameterized function do we want to learn? So this will be the first question we have to answer. Just to mention the applications, as soon as we have a policy that is similar to the expert one that we have observed, we can do decision making, i.e. implementing directly this policy. But we can also use that for prediction, because then when you come to a crossing and you see a car, you can say, oh, from my observation, I know that humans tends to act like this, so I can predict the behavior, or at least estimate a prediction for the other car. So the goal, the formulation, will be to find a generative model that yields trajectories that are similar to the observation. What does that mean, similar? Because you want imitation learning, it sounds like it's about, there are some notions of behavioral match. You want to have similar behaviors, true, but what for similarity metric are you using then? That's the second question will be answered. And generative model, because you want to learn this model. So let's answer the first question. First question is how to describe the task. The task is driving, true, but which model will capture the demonstrated behavior? Is it, this is the first option, the policy, or is it the reward function? Let's go about the policy. This is the direct method, because at the end of the day we want a policy. So let's go for this mapping. We want to derive the mapping from state to action, and this will be the behavioral cloning part. We want to try to understand and model and learn this mapping. The second option is you are saying the model that captures or that describes the demonstrated behavior is the reward function. And you will be decomposing the task of finding the policy into 2 steps. First, you want to recover a reward function, or to find one, and then based on that reward function, you want to derive the policy. Note that the second step, we are already having the tools to do that. So let's formulate that a little bit in another way. We make first the hypothesis, the assumption that all goals can be described by the maximization of expected cumulative reward. To put it another way, is that we assume that the expert is trying to act optimally with respect to some reward function. This is a strong assumption, but let's assume that. Once we are doing that, there is this reward function we don't know. But let's recover this hidden reward function. This would be the most challenging part. And the last one would be a little bit easier because once we have a reward function deriving a new optimal policy, there are many algorithms up there. Why not using, for instance, the one like these tabular methods? This is already available now, so we'll be able to find an optimal policy given the reward function. So these are the two, let's say, the two ways to describe and capture the demonstrated behavior, and these are the two branches of imitation learning I will be speaking about today. Just a very short term, it's called apprenticeship learning. If you meet that, this is basically the combination of that two there. It's about deriving a policy that has been derived with inverse reinforcement learning. So IRL will be about finding this reward function, that's first part. And if the goal is to find a policy, then sometimes you will find in the literature about apprenticeship learning. So we mentioned the two ways to describe the behavior and the task, either capture inside the policy or inside the reward function. I will be going through the two approaches in a moment. Just maybe right now ask, can we already make a short comparison of both approaches? There is this quote: the reward function rather than the policy is the most succinct, robust, and transferable definition of the task. I think it's explicit by itself, but just mentioning succinct, it's about compactness. If you were for a policy to mention all the possible states, then for each of them, you have to say what action to take. If you go back to the example I was showing, there were about, let's say, 20 rows in the Q table, as opposed to the let's say the size 5 vector that I used for the reward function. So it's just mentioning, keep that in mind. The robustness is obviously about the generalization capability, domain adaptation, and so on. I've already touched that topic with the fact of what happens if you meet the first or a state you have never seen before. Obviously, tabular RL is not, let's say, not very good for this particular point. You better have to use some function approximator. I will be coming back for this topic for the BC part in the BC section. Just mentioning about the robustness, you get, I don't know, if you misclassify, because it's this supervised learning, this behavioral cloning idea, if you take a wrong action, the BC will say this is bad because this was not similar to what the agent or the expert did. But there might be some midly undesirable behavior, like you are breaking, although it was not useful, and extremely undesirable behaviors, such as collisions. And if your prediction is false, I'm not sure if in the behavioral cloning part you can distinguish with them, which is not the case with RL, where you might get punished quite a lot if you decide to an action that leads to collision. That's the first part. One could also say that RL is an optimization, like about a global optimization about the expected return on the trajectory rather than the local instruction for each observation. What does that mean is that RL might, or IRL in this case, might look a little bit more appropriate when it comes to sequential decision making. So not one shot, but sequential decision making. And transferability, just cars have different dynamics. If you were to learn human to walk at a given pace, obviously we don't use the same step frequency, step amplitude. So having just a mapping from state to action might be valid for one particular person, but that might also change within the time as your legs are growing when you go from child to adult. So that for one particular person, for one particular time step, On the other end, the reward function, it's a little bit also the compactness, would be exactly the same for all people. You have to reach this target speed and then keep on that. Yeah. So just I like this quote to compare these two approaches because before we go more into depth in two of them. All right, a very last word before we go to the two approaches. What about our expert? I've never, or I didn't explain what expert we use. So it's basically an external code I've taken, and then I put some Python wrapper so that it can interface with this path decomposition, path velocity decomposition, but basically using the stem state and then outputting a throttle value. Just mentioning one, I think, interesting fact. These are, so the top one is showing the speed over this long road over the time. So it's expressed in meter per second. So 9 is around 30. So it's a little bit above that. What you can see is that with the smooth version, which is in orange, is actually the same as the blue one. That means, yeah, it was already smoothed in this in the middle. So it managed to keep a constant velocity. How did it do that? You see on the bottom the throttle command. So at the beginning it was a little bit of binary commands, but then it converged to some 0.6 or something value. So we are there, over there. What I just want to say is remind that acceleration is not throttle. In this case, you have a value of throttle equals 0.6, which is constant, and it's between 0 and 1, so you are more than the half, and that just serves the constant velocity. It doesn't speed up at all, even though you are more than the half of the throttle. So just interesting fact to notice. All right, let's go to behavioral cloning. I think I've already said a lot about that. The similarity metric that we'll be using is this distribution from state to action. You can do regression or classification. Anyway, you collect first, for each time step, a state and an action. That might be, for instance, a video. You have your dash camera, and that will be your state. And at the same time, you make sure you synchronize your recording with some decision, I don't know, the angle of the steering control. And then you build this table. This is actually your data set. And what you want to do is then a regression problem in which the, let's say, policy parametrization, that means the parameters of your model, you get them by maximizing the likelihood of the action taken in the training data. All right, let's do a very basic example. I think you can't find any more simple example. We'll be, again, using Carla, using the scenario with a following leader. Here, what the state would be is basically the distance. So in this case, that's distance over there. That's it. That's the state. So we'll be recording our expect driving, and for each time step, I will be recording that as being the state. And then for the action, I will be recording the speed, time speed. And when you do that, so you can ignore the red dots over there for a moment. The blue dots you can see here is S, so to say, and here over there it's the action, the target speed you have, or the speed you drove. And I've let the expert drive over all of the 10 scenarios where you have to follow leader. What you will notice there, and this is where the red dots comes into the story, you could, this was really quickly made, try to cluster or cut or distinguish some regions. Something interesting is over there. You don't have any expert demonstration how you should act when you get, let's say, 12 meters or less close to the other vehicle. In the same way, you don't have any idea what to do there. And even there, at this spot there, it's quite ambiguous. What should I do? Should I copy that part there, and that one there, or that one? Just to mention, this will be some issues about the distribution of state not being the same as for training and for testing. All right, for the training, I use a regressor. In this case, it was a linear regressor with a polynomial of degree 2, so you can see a nice parabol over there. I was quite happy with the fitting, so I said that was enough. I also tried some decision tree regressor with degree 3. Again, that was enough. And what you can see there is the actual decision that you would be taking if it were in this given state. So if you say, all right, you are at 30, what speed should you have? And it will answer something like 17 or so kilometers per hour. I have to admit that I need, because the curve were going that way there, so I have to clip. It was the first incorporation of knowledge, as I mentioned that previously. I had to clip manually because it doesn't make any sense to have a negative speed as target. In a similar way there, if you leave that like this, because you have no idea, it just decides, I guess based on that one, that all data points should be at speed 2 kilometers per hour. You won't manage to complete the scenarios. Why? Because as soon as you come close to the vehicle, you won't stop. You will drive at 2, and eventually you will crash to that. So I had to make that to 0. Again, this is not so generalization, or this is not so proper learning. Just to mention again, it was just an illustration, and here I had to include some domain knowledge or some external knowledge to make it work. All right, I've been testing it in a different environment. Again, I'm not showing everything. Just maybe interesting to see the code. Here I extract, make observation. I extract the state, which is just the distance in that case. And then I made this clipping, and then I apply the target speed to my local planner, which has a PID, and then I let the PID control or decide what should be the throttle to do that. And then we managed to complete the different scenarios about following a leader and stopping behind it. That's it. All right, that's it for the behavioral learning part. What lessons can I take as a summary? The first one is, at least in this very basic example, it works, and it was quite straightforward, or at least quite quick to implement. Not too much parameters, quite convenient, so it works. The question I have, and I mentioned that previously, it's what happens when the expert is in a case where there was no demonstration. Basically, when you go to a new road, or even based on new proper action, you might say, oh, I still have a wonder. I make a strong decision, and you start going off-road. And once you start going off-road, there is no demonstration at all, because the expert was behaving perfectly, staying on the road. And it becomes very critical, because you are encountering the so-called cascading error problem, where at each timestamp you will be doing some actions that takes you off the road, because you have no idea to recover. You were not shown how to recover. So the cascading error, this is an issue, and this is caused or due to the distributional shift. That means the shift between the distribution of training and the distribution of testing. The agent has now encountered such scenarios where it was to collide, or were about to go off-road, and it didn't show how to recover from this offset. What can you do against that? You could rely on the extrapolation, interpolation, saying, okay, maybe you can interpolate, but that won't save you from recovering of off-road. You can do some data augmentation. That's quite easy to do. You have to do that when recording. This is the ID. Instead of using just the front dash cam view, why not at the same time recording the other two on the side, the lateral one, and say, if you meet this case, then you really should go back to the center. So if you meet the case of the left camera, if you see that, so you probably see one of the pavement over there, then you really should go right, and that will recover you. So that's a elegant, I find elegant way to, yeah, and you will then make your data set a little bit richer. What you have to do also is make sure when you're training, depends on what the expert agent made. But if it's only straightforward and sometimes, very rarely, some turns, then you might have some, let's say, quite unequal cases being represented. So you want to balance them as well. There is another kind of augmentation, which is, let's say, more online as opposed to offline, where you just recorded more stuff during the recording part. Here, Dagger, which is dataset aggregation, is the following. You start training, and for some reason you have no idea, so you start doing something which takes you a little bit off-road. And that where the cascading error could start happening. But what you're doing there is you're saying, I do this action, and then you get the feedback. So you are querying the expert, which is for some reason online available. For this particular case, what should you, expert, do? Or what would you be doing? And what should I do? But not necessarily online. You can do that afterward, but that's better if you do that online, because it's then, let's say, closed loop, then, because you can track your own trajectory and enrich. The idea is to enrich the data set by some state that you are exploring, and the action, what you should do, are given by some available expert. Might obviously become a little bit hard to scale or to organize, and if it's like real-time exploration, but that's the idea of Target, shortly said. Right, a short about the application. From my perspective, it looks really powerful to do this lateral control, where you keep the car on the road. Again, it looks quite promising when it comes to follow a desired velocity, stop behind like a basic control. But as soon as you go in a higher level abstraction, as soon as you have some long range goals that you want to achieve, which implies some, yeah, an horizon which is higher in terms of time, you want to plan ahead. I'm not sure this behavioral planning approach scale robustly. This will be my concern, but really powerful and simple for low case and control level, low level control. And now I just want to raise a question, or at least this was a question I was asking myself. You maybe also ask that yourself. All right, now let's assume we have the ability to track our path, so lateral control. How do you cope with an intersection then? Yeah, I'm just leaving that to you. You can go left, right, and so on. You were learning how to stay on the road, but that would be also nice to decide where to go. I will give the answer in the paper side, in the paper part, just raising the question right now. All right, and just maybe giving one example of this augmentation over there. In this paper, you can see that you have the front camera over there, and then what you do is you have the right camera and the left camera also part of the data set, because if you see that one there, you know that you should go left in order to recover and go back to the middle of the road. All right, that was it for the behavioral planning part. Let's go to the case where you said, actually the model that captured the best the task and the behavior is not the policy itself, it's inside the reward. And that idea is called an inverse reinforcement learning. The idea is you first assume that each participant on the road, for instance, in the case of autonomous driving, is acting optimally with respect to some reward. They have an internal reward function, and the goal is to recover or to estimate it. And then once you have it, you just use the MDP solver to find optimal policy. Not this term was trying to act optimally is not the same as was acting optimally. So we will need at some point some notions of probability. How likely is it to be optimal? because the strict assumption of the expert acting optimally might be too strong. Right, the next question is, we want to find R. This is the new goal. We will be parameterizing the R function as being the combination of linear features, so similar to before. Here the notation has changed a little bit. Here these are the features. Take state action and then you extract some information. You make the dot product with the sum vector, which is the weight vector, and you get the reward that you have to apply. Now I just want to mention a little detail, is that so far we said that state and action are the arguments of the reward function, and that comes to that point there. It might not be a consensus in the community. Some people are saying this is enough to consider S, it should be S and A. Some are even going for SA and S prime, the next state you are ending up, and this is why you get some, there are screenshots, stuff like, so the reward, capital R, but it's a reward for one step, is the dot product of the features, time the feature vector, but it's only function of S. That's written another way, where you have, it's not F, it's not phi or psi, it's another character, which is the first feature multiplied by the first weight, and so on. And instead of having W here, it's just alpha, and instead of having F, this is this phi. But basically it's just dot product, and again function of S. What you can have is function of SA, again another notation. That's interesting to see diversity. This is similar to the weight vector. This is our feature vector, obviously, and then you can write that as a dot product. What is important to note is that, yeah, you can parameterize then the reward function by R, and the task really ends up or really boils down to finding these parameters, the weight, because the feature will be defined, and now the goal is to find the weight of the reward function. And the last form, when you are considering S and S prime, I took it from another paper, although I'm not really sure if it's consistent, because here I guess you should expect having S and having A and S prime as well. This is just a, and again, what is I? It's not really clear. All right, before we go to the optimization, now we want to find the W. That's really our task, to find the W, the weight. We need features. We'll be talking about them. What I want just to say here is that why not doing some grid search? So this is an example of a student project at Stanford this year. What the student did is compare two approaches. The first one over there, where you, let's say, incorporate the human knowledge of typical reward function structure, the goal being to maximize the safety and the mobility objectives, which was the efficiency. And then was a second approach where no prior knowledge was put. The model was a polynomial reward function of S and A, and it was quite a short problem, or a small problem in size, so you could afford then making a grid search, and actually it was showing the best performances. So that's an option if your state action space is small enough. All right, now what for feature? I just said that we want to recover R, and R is the product of some weights vector together with some features vectors. The features should be defined. We had a first proposal for the RL model free case. Basically, they should represent some things we want and some things we don't want. That's why I was coloring that in red or green last time to show the sign of the contribution with the weight. Some time later, we'll be seeing that the features are also used for similarity measures, so not only for reward shaping and defining what we want and what we don't want. In this case, features should capture relevant properties of the driving types. Some examples, what I've seen in some papers: speed, obviously, then you have distances, and then you can derive time from that. What I want to say in this case is that it's usually relative. So it doesn't make any sense having, or it doesn't make too much sense having absolute values. I mentioned the 30 kilometer case where you want to generalize independently of the speed limit. but it also applies, like you can have speed deviation compared to the speed limit, speed deviation compared to the other participants' speed, and so on. And the same applies obviously more for the distances. You want the distance compared to the other objects you have detected, and so on. Based on that, you can derive time. As said, there is you might find the TTC quite often in the, TTC, sorry for that. In the literature, it's time to collision, but it can be anything there, time to crossing, and so on, or time to coming in a zone or whatever. And sometimes you need the inverse for some computational reason. Yeah. And together with this temporal and metric size metrics, you want to use some comfort, or you would like to use some comfort aspects, such as the derivative of the speed, or the second derivative of the speed, which is the jerk, both in longitudinal or lateral orientation. Let's see another example, which is that one there. So this is our car in the middle. The state by itself should be, or could be, sorry, something like you have an obstacle over there, you have an obstacle over there. So this is the state, and we said that from the state we extract information, and that are features. So you can imagine having some field of view or some sensors which measure the time to travel, and it can be bouncing against obstacles and come back. So in this case, you get this measured over there, which is not the usual one when you have no obstacle free, or obstacle when you have no obstacle. In this case, it will be the longer one. And what you can say is that, for instance, phi1 or f1 over there is just the percentage of the full. So in this case, might be here 0.4. This will be your, it's quite hard. Yeah. 0.4 would be the feature for this first component. This one will get 1 because there is no one. This one might get 0.6, and so on. So this is another possibility of vectors. All right, and just to remember last time, or at least for the model free agent, what we have for features, we had 5 of them. First one being constant, always equal 1. Then we had some we don't actually want to occur too often, which is high speed and a small distance. Then we had this one, which was important, which was, are we trying to speed up while being quite close to the other one? Then we had another things to avoid, which is over speed limits. And finally, we had something we want to promote, which is, are we accelerating? And what we said that I made the choice of having them binary, so either 0 or 1, right? And then we had this weighting factor. So these 5 elements, you get them as soon as you are an NS and an A. In other words, you get them at each time step. All right, and the idea, yes, here is to stack them. This is for T0, this is for T1, T2, and so on. And then you can do several things. You can either sum of them, sum all of them, or make the average, so the empirical mean, and so on. That's the example when you average it. What does that mean is that 100% of the time you have the feature 1 being activated, which is obvious because we say this is constant, always 1. The interpretation for that one there is that 70% of the time, the agent that produced that was trying to accelerate, or was having throttle being superior to 0.2. And here is that 15% of the time was the situation where the agent was somehow close to the other vehicle and at the same time trying to accelerate. This is the interpretation. So we did that from one trajectory, but here what I want to say is that you can do that for, like, you can abstract or you can generalize that for any policy. Because given a policy, what you can say and what you can do is, all right, let my agent run with this policy, so it will listen to the Q table, act accordingly, and so on. You will collect at the end of the day one trajectory, and then from that one, or in parallel, you can compute such feature expectation, which is the vector over there. So just remember, given 1 pi, you can generate many of them. Many means as many as trajectory you have. And then you can make, instead of one sample, an expectation over there. And this comes this term, expectation over pi of the feature expectation SA. Right. And the second thing I want to say is the relation with the reward. So this term with the expectation can and is usually noted with mu. So mu of pi, this is function of pi. And it represents, in this case, this is the sum, this is not the average, which is also discounted. This is the feature. One other difference is that here they don't have any a, but you can also think of it as a. Yeah, and this is the expectation you have for the above weight. Sorry, excuse me, for the above feature expectation vector. And then what you can do is say, what is the value? What did we say about the value of pi when you start at at S0? This is on average how much collection of reward you will get. Let's put there on average because of expectation. You listen to pi. How much do you expect of some of reward? Now we are saying that this reward is the linear combination of a weight vector together with this feature vector. And then you notice that T is only inside F, so you can take W out, and then you get, so W is taken out, and then remains the term over there, which is nothing else as mu. In other words, we have managed to express the value of the state as function of the weight vector and the expectation on the feature vector. This is this relation over there, which is linear because of the combination because of linearity of the product, and the assumption that one step reward was the linear combination of a feature with the weight vector. This is the second thing to remember. And this result is very important because remember, the goal is to find a policy where you get the same performance. And an important result is brought by this, let's say, pioneer paper, where the following result is, for the policy to be guaranteed to perform as well as the one of the expert, then it is enough if you are feature matching. So if you match the feature expectation, then you will get a policy that is not worse than the expert's one. And that results in the following. The problem is reduced to finding a policy pi delt that induces feature expectation that are close to the one from pi e is the pi expert. So the goal now is to tune our R is equal to W times F. The goal is now to tune the W so that the expert that is optimal for R, which is that one there, has equal feature expectation than the one from the observed expert. That's the feature matching concept, and that's the goal, how to find the W parameters. To put it another way again, that's answer our second question. How do we say that pi e and pi tilt are similar? The measure or the metric for similarity is this feature expectation vector. And the goal is to find, again, this W or another notation over there, such that the reward function that is here, when you act optimally with respect to that, then you get this pi. You get an expectation that matches the feature expectation of the expert. So here is a star. I was previously using E as expert. And just to mention, in this initial paper, one of them, there was a good illustration of the features. It was saying the following. It was observing the taxi drivers, taxi cab, and then they were crossing bridges, they were driving on certain roads and so on. And here's the following. If a driver uses X miles of interstate and crosses Y bridges in a month's worth of trip, the model should also use this X quantity miles of interstate and this Y quantity of bridges in expectation for those same start destination pairs along with matching other features of significance. So that's the intuition behind it. You're saying that two agents are similar if after they have been performing their rollout, you have a match in the feature expectation and the feature average. Again, the formulation, we want to find the W such that you have this match in expectation. This is the constraint of our problem, the solution being W. There are one issue, or at least one big issue, which is the ambiguity in the formulation. What if W, so it should be size 5, what if I put 5 zeros? Well, that means that whatever the feature, the reward get to R will be equal to 0 all the time. Whatever the action, whatever the feature, whatever the policy as well. That means the return being 0, and that means all policy will get exactly the same value. That means that whatever the policy you take, it has exactly the same return as the expert one. So that means that any policy will be optimal. In other words, with this particular case, this is a solution where you are matching exactly the constraint above. And you don't want that. You want, because you know this is a trivial degenerated solution and you want to avoid that. The solution of that problem is the following. You want to keep the constraint. This will be part of your problem definition, but you want an extra task in addition so that you can discriminate and only keep the good or the best solution. The first option is to apply max margin, where you're saying together with the feature matching, I want the policy that outperforms all the other policies. And the second one we'll be seeing is the max entropy concept, where you're saying again, I want to have this feature matching constraint, and then I impose, or I want to optimize the entropy of the entropy above we will need to introduce some probability distribution and the probability of a trajectory under the given weight, and this probability should have the maximum entropy. Just to mention, we have a constraint, and now we add an optimization objective in order to get rid of these ambiguous solutions. Let's go for max margin. The idea is, or comes from the optimality that we assume for pi. So here we assume that pi was optimal. Was not trying, it was optimal. And now the goal is to find a reward function so that the expert value function is best for the expert demonstration. That means whatever agent you suggest or you propose, I want the reward function to be such as the expert was the best one. You can't find any candidate which was better than it. And if you follow this goal, if you follow this objective, then you end up designing the correct W, the correct reward function. So to phrase that, here is just function of A, so it could be also A. We assume a linearity between a linear combination of features. This is F, this is our W, and this gives us the reward. And then, this was the feature function extractor. And the goal is to find a given W such that when you make the product, so A again is mu, then for the expert policy, so this is this guy, you're better than any candidate. You can have many candidates, and you have an optimization constraint, a constraint optimization where you want it to be maximal. So this is the value, remember, because of linearity. And what you want to do in practice is you want to maximize the margin of the difference. Here we have the expert one. Here we have the one from J, which is a candidate number J, and the difference being T, and we want to maximize T with the constraint of W being regularized, so not having a norm greater than 1. Okay, last slide with the theory, and then we go to the practice. This is a iterative algorithm. At least this is the one possibility to solve that. What we'll be doing is the following. We'll be alternating between two stages. We start with some candidates, random policy, for instance. That might be an option. Then from them, we apply this optimization where we want to maximize. It was called T before, now it's called gamma. This is the margin. We want to maximize the margin, which is the difference between the expected value for the expert and the expected value for, in this case, we have only pi 0. And when we solve that problem, then we got a reward function because we get W. So at this point, we have a W if we have solved it. Then based on this W, we have a R, which is RW. And then we apply the model-free algorithm, the Q-learning, and we get a new pi, which is optimal for the given or for the current RW. And what we do is this pi, we add it, so it's append a pushback to the set, and we enrich our collection of candidates. And then we iterate again, and we find a new W that makes the experts being better than any other one by a given margin, and we optimize this margin, and then we get another W. We get RW, we get a new pi, and so on and so on. And when should we stop? We stop when the margin, although it's optimized, can't be greater than a given threshold. That means we have reached that, and at this point we just read the W that is corresponding to, and then that's the solution. So here is an example. Maybe you remember the numbers, but here is the feature expectation of our expert. So this is why it's called mu, feature expectation of E. We actually take the average and we say this is the empirical mean, so from a trajectory derived. 1 because of constant feature, 0, then we had 15% of the time it was accelerating while close, and 70% of the time it was accelerating. Then I trained the policy with some arbitrary W. This is, you can think of it as the model-free agent that we had in the first part. And then I roll out some trajectories. I compute the feature expectation, and this is this vector. So only 2% of the time it was accelerating while closed, and half of the time it was accelerating. And what you can do is the difference of them. What you see is that actually it was obvious, but actually the expert had a little bit of this feature, which was accelerating, and actually the expert had a little bit of that one. So from them, and having said what the max margin ID was, what you want to do is increase, or at least have a big reward for F acceleration, for F that, because you want the expert to be better, or to be better evaluated. And since he has more of that particular feature, you want to reward that more. And in the same vein, you want that one there, the F, to be positively rewarded because the expert had more of them. This is for one candidate. Then I repeat that again and again as the iterative loop describe that. This is why ... and then I got my last one there. Again, this is exactly the same expert vector. This is a n+1 candidate with different numbers, is only 13% of the time. It is not necessary to be optimal. It can be also random, but it's better to have good candidates, so to say, competitive ones. And again, the difference. What you can see is, or what you can observe is that it's pushed in the same direction. You would like to favor that, the two numbers. Yeah, although there have been others in the dot, this trend was always observed. And then I run the quadratic programming solver on that. Quadratic because you remember maybe you had this norm of W, but it was the norm 2 to be smaller than 1 as a constraint. Smaller than 1. Yeah. So it was quadratic on the one, can do linear of 1. And this was the result as expected. Let's have a look. This is positively rewarded. This is positively. Because again, you want to make the agent better than the others. Why negative? This was because there were stuff in the ... where the expert was having less of them. You see the expert has no feature 4. It's enough to have one candidate having a little bit of them, so that the solver said I want negative, and the same applies there. And here 0 because both expert and candidates all have 0. What a final thing I can notice is this 0.64 or 64, it's actually when you apply the new weight to the expert's feature expectation, then you get this number. And then you can do that for all the candidates. So it was 0.11, it was 0.42, and you can do that also inside the ... And what it shows is just to understand what the solver is doing, or what the max margin is doing, is finding a W, so that when you do the dot product, the number that is bigger is for the experts, and this number is maximum, at least the margin compare. So the 64 compared to 11 and the 64 compared to the 42, there is no other W that can achieve that. Again, remember there is so there is other there were other candidates taken into account by the solver when solving that. All right, and if I follow the iterative algorithm that I just described, I should repeat that and over until actually this margin over there is and over there get smaller than a given epsilon. And at this point, if it's 0, then I've been matching the feature expectation, and if not, it's small enough, then we can afford to stop. And then we have we have managed our task, which was matching the feature expectation. And how did we do that? By the max margin algorithm. That was the idea. So I managed to do that again and again, maybe more than 10 times, each time deriving the optimal agent and so on. But I never, okay, my agents were really bad actually. And the reason, if you look at the reward function, it was promoting the agent to speed up, which makes sense, but quite a lot compared to the other. But the worst is that one there. It was promoting the agent, encouraging the agent to drive or to accelerate when closed. So it resulted in the agent always crashing. And why so? Because the third one, the third in the feature, this is exactly the third component in my feature vector was this stuff about are you speeding up when distance to others smaller than the threshold? And the acceleration was something different. And then I thought, what was the issue with that? And yeah, my conclusion has to do with the binary, let's say the binary nature of the feature. I explain why in a moment. So here's the graph of the speed for the expert. We already saw that with a smooth transition, and then a very stable plateau in terms of speed. In comparison, that was the optimal agent that I demonstrated in the first part, the RL model 3 based agent. You see the speed was a little bit more wavy, and the result, this is the result of this control, where you see that 0.6 constantly maintained, resulted in this constant speed. On the other end, the agent was just alternating between 0 and 1 for the threshold value. Yeah, and that, what does that mean is that the expert was able to explore some continuous like the full continuous range of throttle from 0 to 1, whereas let's say the RL or the candidate that I generated were just able to do some binary 0, 1 throttle. And then this is due to the PID. This is the structure of our agent. This is the structure of our expert. What I've noticed now is that the agent is just able to make some binary threshold, while the other was able to take advantage of the full interval. And then that's problematic when you define such a feature, because this feature is actually making a threshold. This would have been valid if we always had this 0, 1, 0, 1, 0, 1, and you know that it's either 0 or 1, then having whatever value between, and then saying if it's superior, then it's activated. If it's below this threshold, then it's 0. That would have been enough. But when it comes to this interval, then it doesn't make sense anymore, especially when you're propagating this feature in other features. And this is an int as output. So if you propagate that in another one, which is basically here it is, and so on. So always using features that were binaries, and this doesn't make sense when they are related to some characteristic of the expert being continuous. So the binary features, you actually are losing all the information. You don't capture any information about the acceleration of the expert anymore. And my take of that is that it makes the imitation just impossible. So you have two options: either you change the definition of the feature, or you change the expert by itself and how it acts. In the following, I will be changing the feature and obviously go for a continuous features. Another decision I made for the new implementation was about, or is about, the frequency of decision, and I just want here to raise the concept, or to introduce the concept, because it's quite commonly used or referred to. The credit assignment is to, when you get a reward, you don't know actually in the trajectory what actually caused that, what was beneficial to do that. Let's give me an example. Let me give you an example, sorry. It's all about inertia in the vehicle. At t equals 0, you are stopped. You make the choice of throttle 1. At t equals 1, you are still stopped, and for some reason, because you are exploring or randomly acting, you ask for throttle 0. And then only at time t2, because of inertia, the car is moving. And car moving is beneficial, or at least you get rewarded for that, and whatever action you take after that, you get this reward signal, but this will be credited to action equals 0. So you will get, or you will think it was that because of that. Obviously it can propagate, but at least for this one step, it should have been allocated or given to the very first one. But because of inertia, this didn't happen. So the decision I made is lower the frequency of decision. And for instance, I tried with 1 and 3 and 10 Hertz. What does 1 Hertz mean in that case is that at t equals 0, you make a decision, and then you wait for 1 second to see in which state you end in, and only after this second you compute the reward, and then you give it back to the agent, and that should solve at least what I've presented there. So this is the second, let's say, correction or modification I did. I will also be changing the state space, and this will serve as a next example to illustrate the concept of max entropy IRL, which is the second methods that we need to look at. All right, so max entropy IRL, it's based on probability. Why do you need probability? Two things at least is to solve the ambiguities. Ambiguity about, you remember this zero vector being solution. So you want to add another objective together with the constraint of feature matching in order to get rid of the degenerative solutions. The second motivation is you want to solve the ambiguity of suboptimal demonstration. What does that mean is that so far, at least for the max margin, we have assumed that the expert was acting optimally with respect to some reward function. But what if the human we are observing, or whatever the robot we are observing, is actually trying but not managing to be optimal with its own internal reward function? So that's the, let's say, two intuitions why, to me, using probabilities. Then, yeah, so I said this would be the ingredients. Then you want to express the relation with the reward. There will be different notation. Here is one with the optimality criteria, probability of being optimal given a state and an action. And what you want to say is that this is actually exponentially proportional to the reward associated to the transition. And then, well, what does that mean is that a cost or a reward induces a distribution of a trajectory. It means once you have defined a reward function, then not all trajectories are likely to be generated by the optimal action agent. This is what I meant. So you define then the probability of a trajectory given a reward that you have, given a reward function that you have at the moment in mind. What's the probability of a given trajectory to be optimal? And then you use the previous relation and you get that one. Just consider the difference in notation. So here, this is the trajectory. Theta is just the weight, which was phi in this case. And another big difference is that the author was working with minus costs. So minus cost is the reward. And here you find the term again, but you have to normalize over, it's called the path, but I was saying trajectory before. You have the normalization because it needs to be a probability. What it says is that trajectories that achieve the same rewards are equally likely, and those with greater rewards are exponentially preferred. This is what you want to model. Just another notation: the probability of a trajectory ti given this w on this weight vector is equal to the, in this case where you have the linear combination, it's equal to the exponential of the reward function, and again normalized. And the normalization term is just, you loop over all possible trajectories and you compute that so that it sums to 1 at the end. So the objective is, as stays the same. It's about feature matching now with the probability. So you have the probability of a trajectory time the feature expectation for that. This is under the assumption of having a W, and you want for this W to match the feature of the expert. You have obviously several W's that can achieve that, and some of them are maybe not so nice to have. One example, if we take back the example of, for instance, the taxi driver case I mentioned in the original paper, is that the model could produce plans that avoid the interstate and bridges for all routes except one, which drives in cycle with exactly the number of miles we want and exactly the number of bridges. In other words, this will be still matching the features, but it doesn't seem really good. We, on the other side, we really want the one that satisfies the feature counts constraint, but without overcommitting, so to say. And this is the idea of max entropy. So the max entropy principle, which states if we only care about matching the feature counts, and many different distributions can accomplish that, it's not sensible to choose a distribution that shows preference towards other factors that we do not care about. That's the point. So the new formulation is the following. We are still about matching the feature expectation. Again, for a W, for a weight, we have a reward function. And for this reward function, we have an agent, pi. And for that pi, we would like it that its expectation matches the expectation of the pi expert. So that's our feature constraint, feature matching constraint. And now we have another term, which is, while we are doing that, we are looking for the weight. So this is W. that maximizes the entropy of the probability distribution of the trajectory that we introduced before. That's the new objective. Right, so now we have the problem formulation. It's about optimization. It would be nice to have some, let's say, convex problem where we can apply some, for instance, gradient, update gradient steps with gradient ascent and descent. So I won't go too deep in the math, just the idea how to get to the result. For the max entropy, we will be actually doing some maximum likelihood optimization. So to make the trajectory of the demonstrator having the maximum likelihood possible for this given probability that we have defined. And we want the W that accomplishes that. So if we substitute what we have been writing, so P is this form with the normalization and the exponential of the reward. And then we apply the log, and then we get, so to say, a loss function that we want to maximize. And then we derive this loss function in order to get the gradient. And what the end tells us is this important result, is that the gradient, the gradient is composed of two terms. The first one is really simple. This is just the feature expectation for the demonstrator. So it's called D here, so it's the demonstrator. So for the expert, minus the expected, in this case, expected feature counts or feature expectation under the current W over there. To put it another way, we have the difference, so the gradient with respect to phi, which is W in our case, is just the difference between two feature expectation, the one of the expert that we estimate through samples, and the one under the current rewards. So W induces a pi, a P. And then if for each of the trajectory, you compute the feature expectation and you weight it by the probability of that. So that's an important result. The bad news of that stuff is you have to iterate, or in order to get the expectation, you have to go through all the possible trajectories that are possible. And that's, this is more the expectation, the problem. So the integral over all possible trajectory is a very bad news, either because of the horizon is long or because the state space is huge. This might be infeasible at all. So I've been looking at different possibilities. It depends. There are techniques if you know the transition function. There are techniques of sampling. This was not feasible in terms of sampling efficiency for me. So I saw this paper where the author worked on the IRL for highway, and it was saying that the possible approximation of this second term, so the expected feature value, is to compute the feature value of the most likely trajectory over there, the feature value of the most likely trajectory, instead of doing that by sampling. So this is what I did, and here are the results. Just to mention the algorithm, you start with some initial W, here it's called theta W, and then based on W, you can find the best agent. It's there. Now you have one candidate. Based on that, you get, again, this is the approximation step I was mentioning before. Based on that, you need to approximate the feature for the current theta, and this is the second term of your gradient. And then once you compute the gradient, the first term doesn't change because it's just for the expert, so it's fixed. And then you compute the gradient step, and then you just apply the update of the weight with a learning rate. And then you get a new theta, and get a new pi, and then get a new second term, and then get a new gradient step, and then you apply a new step. And you iterate like this. Either you loop for 1 to n, or you stop when the margin or the difference is small enough for you. All right, so this was a lot of maths. If I were you, I will remember 3 points. The first one is this assumption of the probability given a reward function of the trajectory to be optimal is the following, is just the exponential of the reward that you get, in this case having the linear combination of features divided by a term, and this term is normalizing so that we get a probability function. And then the goal is by max likelihood to get W star, and when you have this objective function, the gradient of it with respect to this W is the difference between the features of the expert minus an expectation, which might be quite difficult to compute. And from what I've understood, one of the possibility is to only compute the features for the most likely trajectory, but it's hard to compute. This is the bad news, or at least the point that should take most of the attention. All right, let's give an example of one of the step in my process. You recognize again the 70%, the 15%. This was for the expert, and then with our first candidate, which was optimal, only 2 and only half of the time. So now we compute the difference, which is the gradient. We already saw that the agent had more acceleration and more of this third feature. Yeah, and when you apply this step, you go from the W old to W new, where it's actually updated. It's not having a new one from nowhere. So updated, so you want more acceleration to make the expert more likely, and you want a little bit more less penalty on the third term. This was the example if I take back the cases we defined previously. I was already saying that this was bad design because of binary features. So we'll show the following. Although this is failing, I don't get anywhere, and then I will go to the next problem formulation. But just to mention, update minus 18 instead of minus 20 and 3 instead of 1. So if you plot that over there, you start with, so let me explain. We have 5 weights, so 5 colors, and here are the iteration, so from left to right. So we start with some minus 20, and here with plus 1, and then we iterate, and here was 2.9, I think, and here was minus 18.7, and then again and again. What you can see is that it really make bonus for the acceleration, and it was still not matching to, it was not managing to close the gap in terms of features, so no feature match. And in addition, it caused the agent to be too aggressive, or at least to only accelerate, and I couldn't get any successful agent at the end, which was not crashing. So these are the feature expectation I had. I was starting with, again, 50% of the time for this acceleration, so the fifth one, compared to the expert, which was having 70% of the time. And yeah, we had this expert having here, sorry, yeah, here, this almost 15% of the time, this third feature. And then when following this iteration loop, I was at some point going above in terms of acceleration, so it was only accelerating, but it was getting crazy in terms of safety. And again, I was just crashing to the other participant, so I couldn't get it close enough. Why might I say I might have stopped there because it was already good enough? That might be an option. Yeah, it depends on the termination, but at least this was the case where the 2 feature expectation were close. All right, so I spoke about this new formulation. Let's implement this now. The main contribution, or at least the main change, has to do with the state space and the reward function. What I said is, I was mentioning the fact that I want now relative speeds instead of absolute speed, and I want them to be relative to some events. So relative, for instance, to the maximum one. This was the 30 km/h in our example, but also I would like to have the reference speed, the desired speed, to be a function of the, for instance, distance to the obstacle. So E over there, it decreases linearly. This is actually an idea I got from a paper coming from Valeo. This is the team who gained, or who was first in the track 1 of the Carla Challenge 2019. A very good paper, I recommend that. And again, all the paper references and the source references are in the description. So I implemented that. So I created now this continuous, so mind the float over there instead of int, where I just return the throttle. And then I was using another feature that I defined over there. It takes 3 things: the throttle over there, the delta to the speed limit, which is adaptive. This is important. This is adaptive. This is not fixed. This is why the profile is so designed, together with the desired speed. And I do the following: if we are above the desired, or yeah, if we are above the desired, concretely if we are over there, or if we are over there, and if we keep accelerating, then I return 1 because the feature is activated. If the speed is too low, and if the speed is not too low, the desired one, I can afford divide by that. It won't be 0, and then I just made that so that it's not 1 0, but it merged the two values, the 1 to 0. So you get not binary signal, but a float instead. And another modification I made, you might say, okay, now you get over there a target speed. Your agent is to output a target speed. Why not, let's say, forwarding that? It's a little bit unfair. So the thing I did, instead of doing that, is I went now get rid of the PID, and my agent was directly outputting the throttle value, because it's quite unfair otherwise, I think. I was also having a aerial agent over there for steering. Yeah, but I might not have time to describe that in detail. Yeah, just now working with delta to reference speed. All right, let's go through the iteration. And now we have only 2 features, the one about acceleration and the one about are we accelerating although we are already above the desired speed. So these are the 2. This is for the expert: speeding up when over speed and speeding up at all. 50. So now you also see that they are, I mean, having 0 as features in the feature expectation of the expert was maybe not so, I'm not sure it was really good idea. So here having them in the middle, I'm quite happy with that. This was the previously weight I was using, so I was penalizing the fact of speeding up while already overspeed, and I was encouraging efficiency with this plus for speeding up. Then I have a first candidate, was actually completing the task, so like model 3 before, was good. So here you see it could have been a little bit more aggressive in terms of acceleration and so on. So now let's see if we can push it toward that in order to match the features of the expert. Again, you compute difference with this strong assumption of the second term being the one of the most likely trajectory. I get the gradient, I apply a step. So I say, yeah, the step is with learning rate 10, split big special here, and I get a new weight. These are just metrics to compute the distance and the margin from before, and these are also metrics to see how well under the old and the previous weights are both agent and expert acting. You see that the weights make both the expert and agent a little bit better in terms of performances, but still the RL agent is still better with this particular weight. Again, I repeated the iteration. So here you see maybe going at the feature expectation of the expert. 60% of the time speeding up is 40% of the time almost having this let's say aggressive case, or maybe speeding up when above the speed. And the agent was first quite conservative with respect to these two criteria. Okay, it's not linear, or at least it's not monotone, the direction of the feature evolution, neither for the weight. But what you can see is I was maybe a little bit too conservative with this -10 and this +1. What happened in the middle is I played with the learning rate. I noticed that there was a little bit of overshoot, or was a too big step, which caused, here you see, if I followed the step, I was defining the agent to have negative for accelerating and positive for accelerating when over speed, which doesn't make any sense. So I went back to the previous point, and then I computed with a smaller, here over there, a smaller learning rate, and another one, and another one, and I was quite happy then having this term over there, which was almost matching the feature expectation with these max entropy methods. Here are nevertheless the profile. So although the features are matching, on the left is the expert, on the right is the RL optimal agent. You can see that, yeah, for some reason the expert was not so smooth during the new demonstration I did. Was with another one that I actually did. But still, yeah, with the agent we get a speed profile. So the top left, sorry, the top right over there, which is a little bit wavy. Again, one of the reasons might be that now I'm outputting directly the throttle, so it's not made by any PID controller to do that. Yeah, but yeah, this was just some additional sources of information when trying to understand what was happening. Now I tried with the max margin because I have a couple of candidates at each iteration, so I was going back to max margin. Again, you compute the difference. You notice that you want to make a weight that is both positive, or is positive in the two components, so that to promote two contributions, that would be the idea of the max margin. So the solver was happy having a solution, and this is the new weight, and obviously it didn't work because it was promoting the fact of trying to accelerate as soon as you're above the speed, which, yeah, causes the crazy behaviors. And it was making the agent optimal, the expert optimal, sorry. But I already mentioned that this is proper to the max margin, making the expert optimal and finding a W for that. And the very, very last thing I did, or I tried, is to take the candidates from the max entropy iterations and then set them in the set or in the pool of candidates for the max margin. This is what I did over there. So we have 6 of them, each of them having a feature expectation, the first line each time, and then running my quadratic solver, it converged and it gave me the new weight over there, and you can already check that minus 0.05 is the best value when multiplying this new weight with the feature expectation, and this is for the expert. So the expert is made optimal or better compared to all possible policies or all possible agents that are present inside the pool. So that's the role of the solver by a given margin. But then what do I do with that there? Because it's just promoting the fact of accelerating when being already closed, accelerating when already being overspeed, and at the same time not accelerating at all because it's detrimental due to the negative sign. So if I run that, I just get an agent that doesn't move, because even if it has explored, because it's penalized to accelerate. So I have no clue. Maybe you get an idea what's going on with there. Let's say my intuition or the feeling I have is when I drew a parallel with the update step of the max margin and the max entropy. In max entropy, you can play with the learning rate, saying how much you want to update your current estimate on the weight. It was actually beneficial to use that when we were converging. But here, with max margin, we not even have any influence on that. It's just substituting And I have the feeling there is a kind of overshoot, like it's going, true, you have to make the expert better, but why not, I don't know, why not making it better step by step? Like admitting it might not be better directly, but going step by step, because here at the moment it's just, yeah, if you derive an optimal agent based on that, you have no chance of completing the scenario, although the expert did that in the past. And accumulating the candidates doesn't help either. So again, if you have any insight, if you have any ideas, please put that in the comments. I would be really appreciated, and I will also post if I get a solution for that problem. Thank you. All right, so we are finished with the second part. Personal takeaways, a couple of them. To me now, I've like my point or my take on these features. If you are doing this assumption of linear combinations for the features, and if you are doing IRL, then features plays two roles. The first one is in the reward function. You want to penalize and bad thing and reward good things, so they should represent things you want and things you don't want. But at the same time, it serves a similarity metric purpose. That means it must capture the driving style, because you are about to model the driving style. So if you are targeting feature matching, the same feature that you need to design must also be appropriate to similarity metric. And sometimes, let's say, as the designer of these features, it's not so trivial how to design that so that they match the two objectives. Another point is, I already mentioned that, but you really are pushed, or at least I was pushed, to incorporate knowledge, because at some point you notice that, right, you can play with the reward function a lot to get it to a particular behavior, but sometimes when it comes to, especially to safety, you want it to stop and very stop. Then you better have to make the reward function simple, to make the states simpler, and just add an additional parallel rule-based mechanism that makes sure the vehicle stops when it's about to stop. Or this was just an example. So embedding knowledge, especially when it comes to safety, this will be something I will be mentioning in the paper section, but it sometimes saves you time and also complexity in terms of parameters that you need. A couple of lessons I always also remember: start simple, try to decompose. Decomposition might be good. Make sure that since you are defining your MDP and your agent and the features and the algorithm to solve the IRL problem, you want to make sure that modules are working. So make sure that the IRL solver, the quadratic programming is working. Make sure that the agent has been successful, model-based or model-free, on OpenGym reference baseline environments, and so on. Then things of have scaling in mind. Obviously, tabular, I need to shift my algorithm. It's not an option if the state space grows up, and so on. Sampling efficiency, I couldn't afford the sampling methods to approximate the second term in the gradient expression. This is still, it's always important. And interpretability. So I've been using a couple of tools in order to understand what's going on. I think is really valuable, in particular when you start a new approach or start to implement by yourself, to get some insight of what is going on. I still have questions, so again, if you have clues for that, post that please as a comment. I would like to know if there are some tools to automate the feature selection because it's based on state and action, right? So you want to extract from these two information some features, and yeah, at the moment we are doing IRL because we want to avoid the reward tuning, but we still have, based on point number 2, to design the proper features that are good for describing the driving style. So is there any way, given the state and some rollout and experiments, to automate the feature selection? Maybe some attention mechanism might be useful. I don't know. Be interested to learn more about that. And the second question is, well, if the goal is just to derive the policy, so apprenticeship learning, I think it was called. Do we need R at all? Because remember, the R was just the intermediate step that we get, so it was the IRL step, and then we were optimizing for that and getting an agent. So to me, it's like I can draw a parallel with the RL algorithm, where you go either direct methods where you directly get the policy and optimize it, or you get for value-based, where you are defining and computing some value as an intermediate, let's say intermediate metric or intermediate quantity, and then based on that you take your actions. And yeah, in this case, maybe you don't need the value, could already do the policy, but as far as I know, as far as I read, the approaches were always trying first to recover R and not directly going to policy. So again, it's just food for thought. If you have any points on that, I will be happy to read them. Thank you. Now let's go to the third and last section. Let's go for the third part. So in this part, I just want to make some, let's say, summary of the recent papers I've been reading, and try to make some analogy or some parallels with the basic notions I've been introducing. So I want to answer several questions. The first one is about representation. I've been using a state vector. Maybe there are some different ways to do that. I've been mentioning at the last slide the idea of decomposition. It's quite better for us to understand, but it might also be more efficient. So there are 2 points addressing that. I've been mentioning many times the idea of including embedding some human knowledge, especially for safety, for efficiency as well. We'll be addressing that in safety mechanisms. Sample efficiency is also an important topic I just touched. You remember the question about imitation learning, how to, on the fly, or how to embed some targets while driving. I didn't give any answer at the time, so type for that. And then making some analogy with supervised learning, so we'll be speaking about additional learning. And last but not least, something important is once you're training with Scala, how do you go down to a real car? This also might be important. All right, let's start with the representation. So it's about the state space and the action space of your agent. So far, we have been using some pre-processed state in the sense that it's not a raw image like in end-to-end, and there are some processing, tracking, and so on modules involved to supply us with this vector of objects. And the same applies to the end part, to the output, where we were first targeting a desired speed, and then this was implementing by a PID. Just to mention the famous end-to-end approaches, which take this as input this, for instance, camera frames, so raw input, and output the throttle, which is really low level in terms of control. This can be broken down. The point of breaking it down is to gain some, let's say, complexity, because then you will not be focusing on perception or control anymore, but just focusing on decision. So let's see how it can be done. First, you can say, I don't go too deep in the stack. I just stop at the middle, for instance, in the sense of I want to output some waypoints. I want to output some desired or target speed. And then this is the role of a PID controller or whatever control system to implement that. So I just outsource the steering control task to some external controller. Benefit, obviously, you don't have to learn how to control anymore. Another benefit is that it can be implemented in several cars, and then the controller is actually car specific, but you don't have to be car specific as a decision algorithm. Last but not least, you don't have to act too often, in the sense that the frequency can be put lower as opposed to the control frequency. If you want to achieve some comfortable drive, need obviously to be higher than the decision one. So it's beneficial as well in terms of time. And that's the example where you target, or where you define some waypoints you want to follow, and then it's just job of the PID to take you there. You can also go the other way around, or at least in parallel. It's either or. It can be also and. What I want to say is that you can detach yourself from the perception and say the following: okay, the camera will be processed, or the camera frames will be processed by some tracking perception modules that deliver then some information from the scene, and then I want this information. There are many formats to represent that. One of them is this bird eye view I want to discuss shortly. It looks like this, or like that. For instance, here you have put one obstacle that you have been detecting by a perception module. Why is it beneficial? Again, you don't need to learn to detect what a car is and so on, so it makes your training easier. Then a big advantage of this particular representation, being an image still, is that you can cope with, or you can deal with an arbitrary number of objects, an arbitrary number of lanes, an arbitrary types of geometry. So it makes the representation of the scene very generic. And you can still, in addition to that, have an additional vector which encodes some explicit features such as the target speed you want to achieve, the distance to the goal, I don't know, some time ratio that has been already elapsed, whatever. You can still have, in addition, a concatenation with some features. So that's beneficial. Last but not least, having such representation, you can manually add perturbation or automate some perturbation, and this is easier than perturbing the image in terms of pixel for end-to-end driving. So what I want to say is that for testing as well, or for organizing the training or the edge cases generation, you can put on this there something tricky or some other participants and so on. So that's another advantage of using a bird eye view as a state space. Let me draw a parallel with what has been recently done by a publication of people from Austin and Intel Labs. It's called Learning by Cheating, and it's actually a good illustration of this mid-end concept where you want to make mid-to-mid. In the case I've presented, but you can do a mid-to-end or whatever. The idea they had is you don't want to bother your agent or to make your agent learn how to see. That means how to extract information about cars from pixel, and you don't want to learn how to act in the sense of control. Just want to focus on decision, and after that, or in parallel, you can learn the other two tasks. But as opposed to end-to-end, this was the concept they were promoting. And here's the example they show. The idea is the following. You want to decompose the imitation learning process into two stages. First, you want to learn to act and then to see. This is why they have this split, this separation. So they have a so-called privileged agent over there, which is first learned separately. It's based on the offline learning, so it's based on a data set that has been recorded, and it ignores the images. So you can say forgot about that during the training phase. Since you are using a simulator, in this case Scala, you have the ground truth about this privileged information, because you are not given the image, you are given that. And then you have the expert action. And the goal is to make a mapping from this representation to the expert action, and to learn to imitate the expert with that respect. So once you have that, you go to the second stage when you have, let's say, your end-to-end agent, and the goal would be not about trying to or learning to decide, but more learning to see, because in this case you will be given that, and you won't be cheating in the sense of you won't be given the this bird view or this map-like view. And based on that, you will be doing some offline and online training. Offline to warm up, so to say. So you will be digging inside the data set of the expert. It's a little bit hard because it will be end-to-end, but it's a good way to start with. And then you go online, and online means you are driving. And once you are driving, you are getting yourself into specific situations where you don't have any references, given by the experts that were collected offline. The experts were not exactly at the same time, at the same space, at the same situation, so you don't have any ground truth anymore. But what you can do is use the fact that you know that, let's assume you are driving to that particular situation, the expert can't help you, but the privilege agent can help you because it has learned a policy, and the privilege agent will tell you, in this case, I want to do, I don't know, steer a little bit and accelerate a lot or whatever. So you are, at the end of the day, creating an oracle with this privilege agent, and the oracle is providing some adaptive on-demand supervision in any state that is reached by the other agent, which is called the sensory motor student. And again, cheating is just for the privilege agent, is not for the green agent at the end of the day. So this was an illustration of the concept first learn to act and then learn to see. Another example, this time from ChauffeurNet, from Raymo, just to illustrate that this bird eye view can be really generic and can be very specific. You can have several channels. Here, for instance, is the map structure, speed limits. Here you see the stacking of traffic light, dynamic boxes, so the obstacle that you have been detected. And at the end of the day, this is the output state, the output action, the output of the algorithm, which again is in the format of a bird eye view. So again, a generic representation, both in terms of space and in terms of history. And you can analyze that, so interpretability is also favored. And last but not least, you can generate on your own some edge cases scenario you want to test. This is how it looks like when it's dynamically rendered. So you see the boxes and so on. It's quite good to understand what's going on and maybe understand why this decision was taken. Another concept I've been recently discovering is this affordance learning, or at least this affordance. The definition, or at least one of them I saw, was affordances are attributes of the environment which limit the space of allowed actions. What does that mean is, instead of having this top view grid-like map or this light map, why not having just some features again, or some numbers that represents all what the decision module needs to have in order to make proper decision. This is my understanding of that. Here this is divided into conditional and unconditional, but basically you have examples of, is there a hazard stop, is it true? Then it's true or false, traffic light, yes, no, speed limit, and so on. And based on that, which is a very compact representation, you could make and you can make proper decisions. There is another kind of, this time discrete distance to the vehicle, so the relative gap you have, distance or relative angle, and so on. So affordances are this kind of information, and learning is the process, as I understood, to extract them from an image, for instance. So another example, so I already mentioned this paper. It was from the winner of the Carla Challenge 2019 about in the track camera only. And yeah, it's called end-to-end model-free reinforcement learning for urban driving using implicit affordances. And I draw a parallel with what I've described about the concept learn to see, learn to act. The idea is first to extract information, in this case affordances, from the environment. So you want to use an encoder, decoder. In this case, the encoder is trained in a supervised way, and it tries to predict this high-level information, which is the affordances, and it uses, you see here, a stack of images as input. So you have two losses or two goals. You want to make some segmentation output off of there, and the encoder should also output some affordances or these high-level information, such as, is there a traffic light? Is the traffic light green or red? What's about the distance to the traffic light? Am I on a crossing? Am I what's the difference with the, let's say, the lateral gap, and what's the deviation in terms of angle. Once you have trained that, it's like the task of learning to see, because you are now able to extract information. The information which is useful, or at least the affordances themselves, are the very last parts over there. So you could use, I guess, some rule based on that, or some RL or whatever, to make decision based on that. This will be enough. What they are doing, and this is the reason why it's called implicit, is that they use RL state being here over there. So this is not directly some affordances. You can use the information, let them flow forward, and see what the affordances are in terms of interpretability. This is useful, but you keep the RL network, or the input of the RL is stopped over there, and it might be able to decode some semantic if you go from the top, or get the affordances if you go on the bottom. And that's the idea. And then you train the RL based on that. Another advantage is that you have compact representation, so you can see already the size over there. It's way easier to store that in a replay buffer as opposed to storing a full image. So here's the video that the authors also published. Unfortunately, I'm not able to play that in this presentation, but as mentioned on the right part, you see the segmented image, which is actually, if you go forward and go through the segmentation line, this is not what the RL agent is saying. It's stopping a little bit before in the pipeline, but it's good for debugging. And then you see again on the bottom part the affordances that you will have, the high level information if you go through the last layers on the second branch. Again, the agent doesn't directly go that, it takes this implicit affordances. I invite you to watch the video because it's really impressive, but I can't. Yeah. You find the link in the description. All right, so we have spoken about the representation. Let's go now to the idea of decomposing the task. So the first one is about hierarchical RL. To me, the motivation is the following. Okay, now you have extracted this top view map, or this top view grid-like image. Now you have maybe this vector of affordances, maybe explicit, maybe implicit. But it really depends on the scenario or the situation, and maybe you are using at least, I don't know, 10% of it sometimes the other 10%, sometimes another 50%, sometimes all the features are important. So what I'm trying to say is that it might be nice to restrict, or to have a representation which is specific to the subcase you are trying to address. And this is one of the motivation of the HRL techniques. What I've understood is that, let's draw a parallel with the state and action. So in the state, you are able to abstract with function approximation. That means speed 30 and speed 32 might be known, but 31, this is a new state you have never encountered, but you can approximate it. So state abstraction, state approximation with function approximation, this is already something known and good with MDP. But what's about the temporal abstraction for action? You could also say, well, I will first be trying to reach the next crossing, and then to reach the next crossing, and these are the, let's say, high-level actions or high-level goals that you decide. And in between, you have some low-level set of actions that you have to define in order to reach these goals, and these are two different frequencies. So let me illustrate. In this example, you have two levels of abstraction. You first have, so actions and options. You first have a high-level option that you want to select. It can be seen as, I don't know, a sub-goal that is selected, and it's selected by some meta controller depending on the scenario. So you have option 1, stop at supply, and option 2, follow front vehicle. So these are the two options that you are able to select. Once you have this selected this sub-goal, then you have an action network that generates low-level longitudinal actions. It's about throttle and about brake. And this continues, like this process of deciding the throttle and the brake, this continues until the point that the meta controller decides a new option or a new sub-goal. So that's the idea of the hierarchical learning, hierarchical RL. Another thing I want to mention is that, again, you don't need the full state or the full information that has been extracted. So it's not illustrated in this particular image or figure, but they have developed some dynamic feature selection where some features are useful in some cases and some are not, and they use some attention mechanism. I leave you to read this paper, again, description if you are interested in the reference. But the advantage is that you select the subset of information you need depending on the sub-goal that you have just set. And this is as opposed to the left part where it's rule-based. So you don't, it's heuristic-based and not learn-based. All right, this was the first kind of decomposition. It was vertically organized with this hierarchy. Now there is a second one I would like to introduce, or mention at least. It's called curriculum learning. So here is one definition. It describes the type of learning in which you first start out with easy examples of the task and then gradually increase the task difficulty. Probably you start the driving license or you start learning to drive with a simple basic countryside road where there is no one before going to the crazy roundabout in Paris or whatever. So here is the idea. I will be implementing a very basic example. We'll be working with first a state about just the speed, because the first goal we want to achieve is learn to drive at the speed limit. This is the first basic task to achieve. The advantage is that then we make sure the vehicle will start moving and exploring for the next stage. So first one, we have a state which is delta to speed limit. And the feature will be, are we too slow compared to the speed limit and we are not accelerating, or are we accelerating where we are already too fast? These are the two features that we'll be selecting. And I want to penalize both of them because not moving when too slow and moving faster when too fast is not wanted. This is the first step. Once we have learned that, we go to the second stage of the curriculum learning, where we now want to consider let's say, avoid the dangerous situations. In the follow leading vehicle, it's about respecting a limit gap for safety. So I will add in the state a new component, the distance to other, and inside the features, I would like to get now the are you accelerating while you already are close? And again, I want to add this term. It's about safety, so it's maybe more important than the efficiency itself. This is the second step. Third one, I also want to adapt in terms of speed compared to the other. So it's a bonus, an additional one, and anticipation as opposed to reactive. So I need a relative measure of the speed, which is meaningful, and then a corresponding feature for the reward function will be useful. Compared to the delta, so compared to the other speed, what's the distance? In other words, are you faster and close? And this is a feature that don't want too much to happen, so will also be penalized quite much. So you start with a random agent, and this is the first part, just about learning how to drive at 30 kilometers per hour, so it's meter per second. It's about 9 that we want to reach. This is with epsilon equal 1. So this is absolutely random actions. And you see it goes up, it goes down. Then we go to epsilon equals 2/3. This comes like this. Then with epsilon equal 1/3 comes a little bit in the shape that we would like to achieve. And then we go for testing. And in testing, what you can notice is that it's around 9, which we would like to get, at least in the smooth version. There are some overshoots, a little bit of overspeed, and then some underspeed, but still it's quite good in terms of efficiency. And important, or for the task that we've set, i.e. try to ride at 30 kilometer per hour. An interesting thing is the blue line, so it's the speed of the time. You notice that the speed quite brutally snap or fold, and this is because obviously we met the other vehicle. So again, the goal was not to avoid anyone. We were ignoring any participant, any obstacle. The goal was just about learning to drive at this given speed, and yeah, we can notice that we crashed at the end. Again, just to understand what's going on here, I've plotted the arc marks of the different states. So the state is just what's about the delta to the speed limit. 0 means we are driving at 30. Here was obviously the start where we are at 0, and green indicates the action that was the most promising, so the one that you should take if you act gridly with respect to your Q table. Is just 70 km per hour, as target is just meaning you want to accelerate. It will be clipped by the PID anyway, and is targeting 0 as speed. So what it says is, as expected, as soon as you're driving faster, then you want to slow down, and as soon as you are driving too slow, you want to reduce your speed. Here, it's quite interesting. What should you do when you get to the point of being 30, at least in the bean, because it's discretized? Well, if you remember in the reward function, I was penalizing the fact of being too slow, a little bit more than too fast. So that's might explain why it promotes the fact of accelerating. All right, now how do we go to the next step? Here you see the Q table. The state space was quite small in size. It was another version where I didn't get the fact of seeing plus 20, plus 10, plus 20, plus 30. But basically, here you are seeing the Q table for the first step of the curriculum learning. What we would like to have is include the distance, but without, let's say, we could stop like that and then go to training, but we would have to learn again and again how to drive to 30. So that's a little bit pity, and this is not what we want. The solution I found was just copy and copy and copy for each of possible distances. You copy let's say the function. I see that as a function that allows you to drive at 30, and you copy and copy. You already see that it depends on the size. You might not want, if you have, let's say, 10 steps and each time 5, it might become quite a big table. But at least for this basic case, it's quite efficient, and it will make the sample efficiency, or at least it will make how many samples you need for the second step smaller than if you were to start from scratch. So here is the example where I don't need actually to go to epsilon equal 1, so I was just using epsilon equal 0.5. You see that it didn't crash so brutally, let's say, but still was not the best one. And then this was when testing the second phase, where he has this nice stop. It was not so bad, so good in terms of speed in this case, but still was not trained. At least it was only trained with a 0.5. So might train it again to get a better and smoother area over there. This is always the case. You want at the same time to learn a new feature, a new functionality, but at the same time you want not to remove or not to forget what you have been learning. So quite sensible or quite sensitive how to do that. We are still in 2D in terms of space, state, so it's not too big to represent that distance, and then the delta to the speed limit. Again, it was very short time for training. what you see is that it wants to speed up only in this portion. What is this portion is when you are far away from the obstacle and when your speed is not too big. I'm still don't understand, or at least it was maybe not trained enough, why it wants still to accelerate when you are close to it. But yeah, this is part of the training process. Well, when incorporating the third component, then we get a state space having size 3, so it's not so easy to show, but at the end, this was one of the profiles I got from the agent being learned. You see at the end there was no crash. Yeah. And this is the video of it driving, but basically the same as the model free agent learned without curriculum learning. He managed to get to the 30 kilometers per hour and then stop at the end. All right, I'm not sure if it was going to the end. Yeah, in this case, I also tried to generalize, and I went for another scenario where you see not the pedestrian, the cyclist crossing, to say surprisingly, and the vehicle, our vehicle, should react accordingly, i.e., not being not learning just the training case, but also stopping behind and waiting for the other to move away and then follow it again. It's a little bit conservative in terms of gap it's leaving, but at least for the scenario runner, how the scenario is defined, was fine to go up to the end and then stop behind the vehicle to complete the task. So you see it. And then the leading vehicle will disappear. This is again part of the scenario runner. When he's happy, when our vehicle has been reaching speed 0, the other disappears, and then we manage, or we get the success flag in the report. Right, that was for curriculum learning. Just as a side note, now let's move back to the paper review. All right, so let's move to the concept of safety module, safety action masking, and so on. One motivation, maybe from the last slide, was all right, could we make sure it actually stops behind? And can we have some guarantee, because it will be important if we go on the road to have some guarantee to make sure it will stop. And one idea I've already mentioned a couple of times was or is to have some action masking, or at least some rule-based parallel checkers that you make in parallel with your learning agent. Um, Basically, when you are training, you have two options, two choices to impose some constraint. Either you modify the optimality criteria, that means you're modifying the reward function. It requires careful tuning. That would mean putting a very, very high penalty in colliding and so on. Or what you can do is modifying the exploration process. That means you're constraining exploration with action masking, and you are forbidding undesired states with some formal guarantees. That's the advantage. Let's give an example. Let me give you an example. If you are the blue agent on the highway, then for the first part, so the top one, there is no point choosing action go to the right. Similarly, action to the right when you are in the second case makes no sense, because then you won't go off the road, but you will collide. And this information of there is someone already, there is the the end of the road, are you right, and so on, it's quite easy to extract. So this rule-based or this rule mechanism, it's not so complicated to formulate. What you want to do then in action masking is remove that actions, prevent the agent from exploring them. There are two purposes. The first one is to accelerate the learning process, because then you won't need, or the agent won't try to go in this direction, looks, oh, this is not good, it won't lose time. And the second one is avoid accident-prone states and ensure some notions of safety, for some safety. There are still a couple of questions, so that while I will go through a couple of other papers, the question you can have is, where do we want to mask? Should we mask before submitting the list of 5 decisions in this case to the agent? Should we want rather maybe to leave the decision to the agent and then mask them after that? This is the first question to answer. The other one is, do we want to discard the fact that we were overwriting the action? Might be an option just to add it to the buffer of experiences, and might be an option just to discard it. Then another question you might ask is, what is tested? Is it the one-step action that I've been presenting here as an example, or is it more that the trajectory that you want to go through and see if this is dangerous, as opposed to one step? And in this case, it would need rollers out, predictions, and so on. And a further question with, what is actually safe? Is it deterministic, like you can decide this is safe, this is not safe? Why not working with probability, saying this is probable to collide with 99%, then I put a threshold and so on. And in the same vein, once you have determined what is safe, what is not safe, what do you do? Because at the end of the day, there must be an action coming out of this stuff. So what if not safe? Do you want to get the second best one? Do you want to say, I just give back the control to the driver if there is a driver? You should also clarify that in your design. So here's an example from another paper coming from University of Freiburg and BMW. Just an illustration, they were saying if the action is considered safe, then we executed it. Otherwise, we take the second best action, and if there is no second best action that is also safe, then we stay in the current lane. This is valid because you are driving on the highway. But that's and here you see the process of checking. It comes. It actually reduces the possible set of actions that are possible, and then you just apply the arg max over the Q function, similar to the tabular case I've been showing. And the safety, is it considered to be safe or not, is in terms of this zone, this region, to decide if it's safe or not. Just another example from Honda and Berkeley. What you can do is not restrain or not restrict that to safety, but also consider vehicle dynamics and say traffic rules and so on. So just to illustrate the fact that it's not necessarily just on safety, it can be on other criteria. And again, here you have the masking part based on the action that you want to apply. Another example from Ford and Michigan University, West Virginia University as well. Here, I just want to point that, again, you have this decision at this point over there. You have a decision coming out, and then it goes through 2 checkers, so to say, as opposed to 1 in the previous cases. You have a uncrafted safety. So it's similar to the previous one, where you have some threshold rule-based if-else condition being checked, and then you want to mask it on that. And you have a second one, which is learn-based. And the idea is the following. You want to determine if one of the future state violates the uncrafted safety rule. In other words, it brings us the intuition of prediction, because we want to roll out, so to say, and what you're doing, because you have no idea what the rollout is that you dynamically learn this safety module, as opposed to the first one, which is uncrafted. You have a heuristic rule about minimum relative gap to traffic vehicle and so on. So you are combining these two safety modules. Another contribution that they have, and I find it quite elegant, is these two buffers where you store the experiences when the RL agent is acting. So you start with a first safe buffers, like classically, it's like the classic DQN one, but you also equally sampled during your update stage a second buffer, which is the collision buffer. And in the collision buffer, you have different ways to put or different reasons why you should put the experience inside it. The first one is if the uncrafted safety module, so the rule-based, so to say, consider that the action is not safe, then you put that into it. And at the same time, if the dynamically learned safety module detects some dynamic collision in the future of the predictor state, again, you would put that in the collision buffer together with some negative term that is, let's say, put to the reward as well. So again, it answers two of questions. The first one is we actually want to make some prediction, and the second one, so some rollout to evaluate if it's safe or not. And the second one is we don't want to discard it. We actually put that in the safety, in the safe and non-safe collision buffers, or experience buffers, sorry, as well as updating the reward signal that you give for this particular step. Let's continue with another one where they go again in the direction of having a prediction module. They want to make some rollout, and the rollout, at least for me, makes me think of the model based. You want to have a notion of the transition probability. What will happen if I take this action of term t? Yeah, what will happen? What is interesting in this paper, I think, also is that they are trying to consider the risk more than, or at least they define the safety as being related to the risk, and the risk has two terms: the harm, how much cost it has if it happens at all, and the second one is, or the second component is the probability of it to happen. And they have a quite elegant way to use that risk as a criteria to decide if a trajectory based on prediction it's safe or not, and if you should mask it, or not masking, but at least assessing it by this additional safety module. So here's another example. I just mentioned this because it reminds us the concept of high-level policy, high-level options. Here they basically have a checker on the options, the sub-goals that you are fixing and deciding, and this checker is based on LTL, so this linear temporal logic verification. Last but not least, this example from Honda, where they have a prediction module that masks the undesired action at each time step. That makes me think a little bit of the tree search technique, where you want to explore the path and explore it until, let's say, terminal nodes, and then find either is safely not acceptable or it is. So two things to mention. First, when you want to do this prediction step, you obviously need to have some model. It will bring us to the next section, which is model-based RL. And the second thing is about, I'm not sure about computational efficiency if you have to do this tree search. I have no idea, but I can imagine it becomes quickly the bottleneck, similar to the collision checker that you have for path planning. Just need to check out if the prediction module might become the computational bottleneck for the framework. And they published, or they're not published, but at least one patent was published from that. Again, you see that the vehicle might apply a prediction algorithm to the high-level option to mask undesired low-level behaviors for completing the high-level option where a collision is predicted to occur. Again, prediction over there with masking and then you have all the options from the policy, and they are restricted based on this masking mechanism. And this sort of prediction, in the sense of MDP or in the context of MDP, brings us to the model-based RL, the motivation being you would like to be independent of the environment in order to, let's say, sample or roll out and imagine what will happen in the next step if I take this action being in that state. In planning, you know the transition function, so this is not a problem, but when you do model free, you don't have this information. All right, so when we are doing a model free RL, the only goal we have is to learn this policy or value function if you do value based. So all the interactions with the environment is to gain experience in order to find and optimize this function. On the other hand, when we do some planning, we actually don't have experience from the environment at all. All what we are doing is we have our model, we do our internal rollback if needed or value iteration, and then we derived our optimal policy. These are this is the other extreme case. And here's the idea. This stuff comes there, and this one comes here. And model-based is from experience. You are squeezing some information from that, or at least you take it and you accomplish a second task, which is building a model. So from the experience, you don't just build a policy or build the value function. You also want at the same time to build your own model of what is going on, and then you apply some, potentially, if you want, you apply some planning technique. These are several advantages. The first one is that it first reduces the interaction you have with the environment. Obviously, if the environment interaction is costly or heavy to organize, this might be quite good for your sampling efficiency. And yeah, this is the main advantage. The sampling efficiency, now you are, say, independent of the environment, and you can imagine on your own what will happen in the next state, or what will be your next state, knowing the current state and current action. So in other words, just to make an analogy with the graph we had before, we were actually playing with a real environment, and now we will be, so to say, substituting it, or at least building our own model, like we are our own source of experience internally that we have built. And this is let's say, a good image for model-based. Well, on this idea can be implemented in the so-called Dyna-Q algorithm. Q because it's based on Q learning, and Dyna because you learn the dynamic. Now I understood that. The idea is similar to model 3 for the first part. Here you select an action, it's epsilon greedy. So really exactly what I've been doing, or I've been doing some salsa instead of Q learning. So far it's model 3. Then you add this step where you don't throw away this experience. You have already exploited the experience to update your Q value, but now you also use it to learn that when you were in S and A, then you should transition somehow to S prime and you should get R. Might be deterministic, it might also be stochastic. We'll show that in a second. The first part. The second one that you want to add is you want to repeat for n time the following. You will be sampling some state and some action that you were already encountering, and then this is missing if you don't have any model, because you can't teleport yourself to this particular state, and this won't be possible. So what you do is you imagine what will happen if you use S and A. What will happen according to the model you have learned is that you will end up in some H prime and some R. And based on that, and very similarly to the update phase over there, you update your Q value. And so the point is, you are now independent. You can on your own generate experiences, and this makes the sampling efficiency better. That means it makes the dependence on the environment less important. This is particularly efficient if it's costly to sample from the environment. So here's an example of DynaQ for our problem. Again, linear combination of features for the reward function. Then we have this constant term, a term that shouldn't happen too much, which is accelerating when you're already over speed, and then a term about acceleration, which is permitted. At the time I was using these binary features. And what you want to do is learn the reward, so it's already explicitly said here, and you want to learn the transition as well. So I applied the DynaQ algorithm, and here are the results. So what you see is so these are the state in terms of speed at the bottom, and what you see is that given the speed, the action slow down, so to say, will lead to -1 on average, because you won't prompt the feature you're accelerating, or you're accelerating while already over speed. So these first two won't happen. The only that remains is this -1 constant contribution. So actually, this was learned correctly. This was the properly learned. And the second one was about you target a high speed, and here what you see, it goes to the -10, which was should be, yeah, you were already too fast because above 30, the speed limit, and you were still asking to accelerate. So this is why it's penalizing. I'm not sure this is exactly it should be -10 -1. Ah yes, but it's -10 +1 -1. This is the reason. So the -10 is because you want to penalize the fact of accelerating when over speed. Then you get a +1 because you accelerate, which is benefits, which is rewarded, and then you get a -1, which cancels the previous one because it's the constant term. So this is actually the correct value. Now let's have a look at the transition. This is the state you are in terms of speed. You're just speaking about speed now. You were at speed 0, for instance, over there, and then the question is for the action, so it's for a given action, in this case for action speed up, what's the probability of transition to state 0 as well, of state 5, and of state speed being here 45 km/h. So what I did is I just counted and then divided by the number of transitions that have happened from that particular state, and then the color represents the frequency of that. So here you see most likely you are to end or to stay in this 0 speed, but you also expected to move, and this is what I would have guessed, move to the next state, which is a higher speed because you've speeded up. Basically what you would expect is that everything goes to that direction, more precisely in that direction, which is above this line. Doesn't happen always. Probably, or at least there is a contribution of the frequency of the decision with the inertia, but that should explain a couple of non-evolving state. But also, if you reverse the reasoning and say you were slowing down, and then only for one saying I want to accelerate, so this would be then part of this table, but it was already slowing down a lot before, and due to inertia this might explain that behavior. Just to illustrate the concept of model-based, where you explicitly want to learn as you are experimenting, learn both the reward function and the transition function, so that you're able to make your own update steps. Well, back to the paper view. Is an example from Michigan and Ford as well, where they have 3 modules. The first idea is you want to learn a model of the environment and subsequently derive the policy based on that. So it's way more complicated and way more interesting than what I've been presenting. They first have a bidirectional autoencoder to encode from a front camera here some abstract latent representation. So you stop at the middle and then you have your abstract representation, so encoder decoder, and then you will be using that in the second step. which is trying to predict, based on the latent representation, what will happen. So you are only working with this latent representation, input, output with that, and this is the prediction. So similar to the transition function, you want to predict what will happen. And then, based on that, they have some CMAES, so it's evolution strategy optimization in order to take action based on the prediction that you have just been outputted. They are given some numbers about sampling efficiency. They compare their approach to the imitation learning, which is behavioral learning in this case, and saying imitation learning was requiring 14 hours of interaction with environment. Then they also have as baseline some model-free RL, which was required 12 days of interaction with the environment, and they are claiming that within 5 hours they were able to have a good prediction, a good encoder-decoder term. They are not saying how much times. Then they needed to look for a good policy, especially since they are doing some evolutionary strategy. And yeah, anyway, their point was to show that sampling efficiency, when it's quite costly to interact with the environment, can be beneficial to use. And it's 12 days for model 3. A second method, or a second example, sorry, of model-based, at least they share the motivation of being sample efficient again. In addition, they have a second motivation, which was interpretability, because they were first starting with the fact that obviously behavioral cloning is not enough, or it's not good enough, because it doesn't consider future consequences of actions. It's quite reactive. And on the other hand, the model-free RL methods are limited because of the training data, or it requires order of magnitude more training data than when the human does when they solve the same task. And the second problem of model-free RL they pointed was that it's like having an unexplainable RL policy. This is bad, undesirable. And so these were the two motivations: sampling efficiency and interpretability. And now they've introduced this semantic predictive network. Sorry, it's close to the MDP, the model predictive control, where you have a model internally, the transition model, and where you seek where you're looking for optimal action sequence, and then you only execute the first of these actions. This is why predictive, and why semantic is because in this case, instead of predicting the future state, they are predicting the next segmentation map. What could happen? A condition obviously on the action sequences you have and the current observation. And together with this future scene representation, they also have some, let's say, task-dependent variables, they call that. So they are there, that they are also predicted, for instance, the speed. So you have different losses. But that's the idea, not only predict what will happen, or at least predict what will happen in the term of segmentation and task-dependent variables. And obviously for interpretability, that might be really useful, because then you can have a look at it and maybe better understand the decision. So that ends up the part about model-based learning. This brings us to the notion of conditional learning. You would like on the fly to influence, to give some navigation goal, for instance. Concretely, when you were doing some imitation learning with behavioral cloning, you were able to follow the track. The question is now, what happens when you come at an intersection? You have 3 or 2 possibilities. It would be nice to have a way from the outside to condition the action, to say, I want now you to keep on doing this job, but take the left or the right option. That's the motivation. So in this paper about conditional affordance learning, we now saw what the affordances are. Here you can see an additional set of example like relative angle, center line distance, is light red or not. So you are learning that and then making the decision based on that. Here what they have is an additional input, or at least an additional component considered by the neural network, which is this directional input. That means now, from now on, the maneuvers are described, or the maneuvers that need to be performed, such as go straight or turn left or turn right, are included in the decision process. Now comes the question, where do you want to put them? What does this arrow mean? You could imagine having them as an input, so at the same point where this stack is coming. You could imagine having the network outputting, I don't know how many options there are for maneuvers, and then only considering the one that is given by the high-level command. Or another option is internally to have some, I don't know to draw it, but some internal gates that are activated or not inside the network. So these are a couple of questions I was asking myself, and this paper is answering some of them. And what they show, or what they claim, is that conditional in the network is better than conditional, for instance, in the controller. So here's another example where your high-level planner, as they called it, basically the navigation module, already knows if you need to follow the maneuver, go straight or turn left or turn right. And based on that, it's injected, and then it goes inside the network. So let's have a look what's inside the network. You have this decision, it's called by D, and then it's a kind of gate which decides where to go. It's not applied to all of the tasks, as I mentioned, not all of the affordances, but yeah, obviously you need to have the relative angle, because when you call, the angle is the orientation. So when you're coming close to the intersection, if you are saying you must go left or you must go right, then the reference angle that you need obviously change, and this is why desired distance to center line and relative angle are influenced by this condition internally of the network. This is a following of this structure about privilege cheating agent, and the other one where you see that actually can produce and see what the different action will be depending on the high-level module that you will implement. So you have these heat maps produced for all of the possible commands, and then the input command that you have, which is over there, the C. This selects the conditional branch that you want to use, and then you apply. In this case, was turning left that was applied. So another example of conditional that can also be used for reinforcement learning, not only imitation learning. In this case, in the work of Valeo, you see the condition that takes place into this part over there. So it comes as an input, as a navigation command, but it actually is implemented inside the network, where when you come at this point, then you are forwarded in one of these directions depending on the conditions. So internal of the network again. Another example, again, you see the command coming here and then going to the conditional module, which influences the action. This time it's not part, or you still have this extractor being independent of the conditional module. Just what I want to say is that here you see the predicted speed, and actually the paper was called, or is called, Exploring the Limitation of Behavioral Cloning for Autonomous Driving. And the concept of speed prediction is you want to learn to predict the ego speed, and the point of that is to address the initial problem, and this comes from the so-called causal confusion. It means you have some data sets collected for behavioral cloning, and when the ego vehicle is stopped, for instance, as a traffic light or traffic stop or in a jam and so on, the probability for it to stay static is indeed like overwhelming in the training data. That means that it thinks that low speed means no acceleration, and this is a causal confusion, as they also explained, and having the task of predicting the speed allegedly helps to address this issue. Again, have a look, but I was quite interested in this idea. And the last example about conditional learning in this case is not imitation learning, it's really reinforcement learning. Is again, you want to at this point inject one of the 6 commands for the navigation, and then it goes and continue until the steering and throttle action you want to output. So I've been mentioning that behavioral cloning was part of supervised learning. As a result, it could benefit for all the techniques and research from supervised learning, one of them being the augmentation, but there are many others. And the question would be, is it also possible to draw some parallel between inverse reinforcement learning and supervised learning, and could it take benefits of all the innovation and ideas that comes from supervised learning? So let's draw a parallel with GANs in supervised learning, so this generative adversarial network, in which you have a generator and a discriminator. In our case, at least for IRL, what we had is a policy which was trying to produce data that was similar to the demonstrator. So concretely, we had these candidates, and then from this candidate we rolled out some trajectories, and from these trajectories we have this feature expectation vectors, and then we aimed at, or they aimed at, producing vectors close to the feature expectation of the expert. So in other sense, we can see the policy as being a generator, trying to produce data similar to the one from the demonstrator. And in parallel, we have some discriminator whose task is to say, does that come from the demonstrator or from samples, from candidates? And that's the task. So actually the reward function is tuned and adapted, and this is exactly or at least this is what max margin is doing, is shaping the reward function so that it's clear to distinguish between what the expert has been producing, is a big good, from what the other candidates have been producing. And then the task is you want to make a binary classification. You want to maximize the log probability of giving true label to demonstration data and giving false label to the other samples from the candidates. And then from the discriminator part, it has a special form, but you still have this ratio. It's P over P plus Q, where P is the probability of the trajectory coming from the expert. And then what you do is you train the policy again to make it better, and again and again. So at the end, what you can notice is that we still have explicitly in the objective function, at least in what we are doing, in what we are optimizing, the reward is still explicitly derived. That means we know it's everywhere, it's there, over, and so on. So it was a little bit my point of questions. Are we able to get rid of that if the goal is just to derive by this process, only derive the policy? We are not interested in the reward function. And actually, from the courses I took, I learned that it's possible, requiring another form of the discriminator, where you just do the regular binary classification, and you get the policy directly, not learning the R. It requires other assumption. It's a little bit of other technique, but it's possible. And a good example of that has been applied to autonomous driving, at least in research, was this GALE method, so generative adversarial imitation learning. The goal is to train the policy again, so that it's rewarded when it managed to deceive the classifier. And the motivation was that IRL itself is computationally expensive, and this is due to the fact that it first recovers or try to recover the expert cost function or reward function. So they are doing some direct policy optimization without first learning the reward function in order to try to imitate the expert behavior. Another example, this time it was more for prediction. What I find elegant is that you still have this structure of discriminator and generator, and that's actually the metric that is behind it is accuracy, because you want one of the objective is the imitation accuracy. That means it has to be consistent with the observed input that you add from the demonstration. And what they have is, in addition, they have another objective, which was it should also be in terms of safety good. That means at the end of the day, the generator is outputting some trajectory. This is why it's made prediction over there. And then this prediction is assessed or evaluated based on several criteria. The one is the accuracy of the discriminator. Does it manage to deceive the discriminator? But the second one is the critic. And the critic has to predict the likelihood of the future dynamic and static collision. Means, is it here you can see -1 because it crosses over there. It crosses the pavement, which is bad. So yeah, this is the having not only as an objective the imitation accuracy. Another good illustration of having additional objectives or additional feedback is this one. So this augmented adversarial inverse reinforcement learning is the following. You have this discriminator d of theta that you want to learn, and then you supply some trajectory coming from the expert, some trajectory coming from your candidate, and then you want to actually update your reward function you will be training on, like the generator is trained on a particular reward function, and this one is influenced by two terms. The first is the discriminator, how easy it was for it to distinguish you from the expert, but you also want to add another term in the reward function, which was how good was your trajectory with respect to semantic rewards. Semantic rewards means in terms of success, in terms of crashes, and so on. So just a good illustration of how to provide the agent with some, let's say, informative guidance in order to assist it so that it learns faster. This is the motivation, learns faster, because inverse IL itself might take too long. And embedding some domain knowledge, in this case in the generator reward function, it's an appealing idea. Just to mention on the top, you have also an example where they were doing some action masking techniques, where only the valid action pairs were allowed. And the motivation was to reduce the non-necessary exploration, once again. Here, a last one about, but actually going in some similar direction. You want to augment the reward. Augmentation of reward, what they are comparing is, you now look at the GALE, they have also the multiple gain, where you have several agents, and now they have the reward augmented imitation learning. And what they show is instead, so in terms of domain adaptation, you want to have some robustness generalization. So you train on a straight road, and then you try to see how it performs well on an oval roadway. And what they have is, just as an intuition, is to augment the reward. You have binary rewards such as do you collide or not, and then you have some penalties saying in advance I can already say that you shouldn't do that because it's undesirable. So again, idea is to incorporate some knowledge, in this case, for domain adaptation. And domain adaptation brings us to the last but not least topic. Yeah, so these are the two, web management and engineering. So now, let's say you are trying to learn an agent with imitation learning on Carla. How do you transfer it to the real world? Well, doing just imitation learning won't work. We already mentioned that with this distributional shift, with cascading error and so on. And yeah, research team have already confirmed that obviously with this quote, pure imitation learning is not sufficient. This is from ChauffeurNet, from Waymo. They have been driving 60 days. It's more than 30 million examples, and that's not enough. So you want to do two things. First, you want to make the transfer from semantic images to real, and to real real views. So this domain adaptation is about generalization. You can do augmentation, obviously on the camera input. What you can also do is have a second goal, which is while you are learning the policy, it's also doing some segmentation, and then take advantage of having to do that as well, the loss and so on, in order to better transfer from virtual to realistic environments. And you train that further online at the same time as your policy. So this auxiliary learning concept. The second thing you want to do, but that you want to do inside maybe the simulation, is to be ready to get ready for edge cases, because the training data usually doesn't have like real collisions. So how can the agent actually learn to avoid them if it has never been exposed to during the training? So one option is to have, we saw an extra loss function. That might be an option. So environment losses should discourage you, for instance, could be measuring the overlap of the position of the agent with a non-road region. This is an option, and that will be another loss function, loss term. The idea is to go beyond the vanilla imitation loss. That's this one. Then there is the augmentation. Again, you can try to perturb a little bit the dynamic, randomize a little bit the dynamic of the car, see how it reacts. You could also expose the model to non-expert behavior, such as what happens if I put you a little bit off-road, and are you able to recover? Are you able to stop at least? And this brings us to the last idea, which is a little bit further than augmentation, which is you want more complex augmentation, for instance, with reinforcement learning, especially for highly interactive scenarios. And this is the concept of you want to simulate the bad rather than just imitate the good. Again, this is from Waymo. You want to have some agent that on purpose are putting yourself in, or putting you in some tricky scenarios, and see how you want, or how you can cope with these more complex situations. Just an example of the augmentation scheme here. It was about this encoder that extracts the affordance, so you can interpret if it was correctly done or not. What they were doing is they were a little bit turning and moving the camera around. So just a short example of augmentation. Here's another one where you can see two things. Again, this high common level, so it's just a conditional one. And then here you have a auxiliary learning. What they are claiming is that when you concatenate, the idea is to concatenate the RGB image together with the semantic segmentation map that is learned offline. When you concatenate both of them, then it's it's better for it, at least it's better to achieve the policy transfer from or between virtual and realistic environment. All right, and a very last example about auxiliary task supervision. Here, they were actually using this idea of having to predict the segmentation map, although this was not the let's say the main goal. The main goal was about to learn the policy to drive, and they were learning this mask we can't see too much, but on the video it was better. They were having a mask such as moving obstacle, traffic light, road markers, road, sidewalk, and background. So not the usual semantic segmentation map that you have in perception, but I think from this little review shows that segmentation is really important in the encoder phase, or at least in capturing elements that are essential for you to make a good decision. All right, that's it for the, let's say, this small paper review. If I try to step back and see what is common in all this work, they all share, or at least they mainly share, three motivations. The first one is they want to make the training efficient. Model-based was an option to improve that, especially when it comes to simulators where, okay, you can do parallelization, but it's still one of the bottlenecks. The second one is about interpretability. Now it becomes a must together with safety guarantee. And the third one is you want to generalize both in terms of scenario and then move from simulation to reality. And the tools that I have presented or that I mentioned, this decoupling the task. You first want to learn to see, decide, and control, at least see and control separately. That's beneficial for the training efficiency as well, makes the task easier. Training a very huge RL network from scratch, this might be quite challenging. So decoupling the state representation, also decomposing the task. This was the idea of hierarchical RL. This was the idea of curriculum learning, making it simpler and step by step. A third one, was about this privileged learning. I was always mentioning in the first two sections, why not including some or embedding some let's say expert knowledge, but instead of do that and instead of explicitly having these rule-based and heuristic algorithms that mask stuff or that take over, the idea is here, okay, you want to make it more efficient and go in this direction or this direction during learning. So privileged learning and having task supervision, such as side tasks or auxiliary task supervision, is I think a direction to look for. And last but not least, we saw a couple of augmentations. Can be augmentation in terms of reward of loss of data set, together with some ideas taken from supervised learning. I know it's taken at least some parallels that we can draw to have some new ideas how to integrate that and benefit from all the work that is done in supervised learning as well. So I hope you enjoyed that. Sorry for the long, I didn't really expect. I'm really tired now, so I think I will go to bed. Thank you for listening. Thank you for watching. I hope it will be useful. I think it's quite relevant and yeah, so making it, sharing knowledge. Also for me, it was quite challenging because I realized like trying to explain what I've been learning that actually didn't understand too much at first sight. I'm still not an expert in that topic. I need to look further. I would be really grateful if you could post some feedback, some recommendation of reading, some maybe videos as well where you try to explain what you have been understanding in your domain. Yeah, I hope it has been useful for you, and see you next time. I just mentioned some papers. They all are listed in the description. These were the theoretical paper for inverse reinforcement learning. These were the courses and classes I will recommend if I were to do that again, and I will try to, again, read more details about them, but I found all this lecture quite well made. 3 papers specifically for IRL for autonomous driving, which I really liked and I mentioned also, especially the first two. And last but not least, let me mention this repository. This is yet another one, let's say, where you have all these categories. I've been trying to summarize the papers I'm reading. It's for me quite useful, and then I thought, okay, maybe not why it's just papers, right? So why not also posting that online so that people can have reading recommendation and yeah, have a first view, select the papers that you want to read and analyze them. So again, I hope you will like that. Give feedback if you're happy with that, or recommendation for other sources of knowledge. Have a good night, and see you next time. Bye.